I have a confession to make. I suck at maths. All right, fair enough. Here's why that may give you a slightly awkward feeling. I've got a PhD in physics. Getting there was quite the journey. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. Imagine yourself a freshman at university taking courses in engineering management. High school is still well within memory, of course, and you find out that you are the only student who is younger than 30 years of age. It took me longer than I care to admit to realize that I would be better off doing something else. I decided to do so. Fine, but what to do? I'd been successful at high school with the following thought. I'll major in physics and math. That's what I don't know how to do, so I can learn the most. I repeated that line of thought after deciding to quit what I considered to be a geriatric class of elders. At the time, I'm older now than most of them were then. The point is, I started studying physics. Goes to show how stupid logic can be sometimes. See, when I showed up in Tübingen in Germany to study physics, I ended up being the only one in my class without a study group at the end of the first semester. As Kevin, which is not his real name, told me once, "You don't fit here either," as I want to add almost automatically. I wasn't enough of a genius, I guess. Still, I decided to give it a shot. After all, how often was I going to change studies? And to boot, I was interested in how nature worked. I did want to learn. I just wasn't very good at physics and maths. And I felt that that wasn't an excuse to stop. Still, I needed something to keep me going during those dark years. Enter 42. The amazingly accurate answer to life, the universe, and everything. I can't say that I know everything. What little I know about life, I try to use as well as possible to make every day count. The universe, though, I could at least attempt to get a hold of the universe. And yes, there was a bit of subconscious hubris in that thought. Here is how we, as of today, think the universe works. In the beginning, there was I don't know what. As the universe came to be, it expanded rather faster than anything you could ever imagine. It didn't bang though. The radiation expanded and cooled, as the saying goes, and no, that's not a proper sentence semantically, but one that's stuck in my head from a melody sheep song. When things cool, stuff happens. Mostly we know this from, for example, water becoming ice, but it's just as applicable to things like radiation turning into matter, because things aren't quite as hot as they used to be. With time, lots of time, things cool down enough for matter to not just exist, but bond into something like the universe we see today. There's a lot of science and story, I might add, bound up in this, and I would very much like for you to read as much about it as possible. It's all a bit weird, to be honest. Scientists check what may be false, and need reasons to think something may be true. The Big Bang Theory predicts the so-called redshift. We found the redshift. It also predicts something called cosmic background radiation, and we found that too. But then, of course, there is dark matter and dark energy. Exploring dark energy and what it may or may not be, I found myself confronted with, of all things, particle physics. If you want to know where stuff comes from, you always end up with particle physics. That would be fine if it wasn't for the fact that we talk particle physics. You know, as I progressed through university, undisturbed by the naysayers, there was just so much that was just so weird that I went from being interested to being intrigued. I mean, you know what I mean, right? For example, you've already heard about empty atoms before, Rutherford's experiment and all. But even though we're factually mostly empty space, nobody can look through us. What's more, we touch things all the time. Quantum reflection makes it possible. Do you know what image forces are? They are quite literally what you feel. They are tangible. When I sat there one night, reading until the morning dawned, I was happy. Past my bachelor degree even, there had been an underlying feeling of dread. I thought that I might have screwed up again. Not after this night, though. After this night, I knew I was going to be a physicist. Honestly, how could I not want to be? If empty matter isn't enough for you, just think about what is called the double-slit experiment. Childish innuendo in that name aside, this is a manifestation of about the most weirdly awesome piece of reality in existence. Depending on how you set it up, particles moving through a wall with slits in can behave either as a wave or as a little ball of sorts, or get this, both and or neither. Talk about screwing with people's minds. This means simply that we become somewhat helpless when confronted with the microscopic world. Imagination surrenders, and yet, as it turns out, we can find nothing less than how it all fits together this way. Particle physics is about the 12 particles of matter, 4 forces of nature, and the Higgs boson. These explain the whole world as we know it. Well, they don't, and I knew they didn't, but what occupied my mind mostly was how humongously unintuitive all of it was. Just take the word particle. It describes one thing in the real world. You know, the kind of thing that you hoover up. In physics, a particle is determined by its wave function, which, when taken to the square, gives us a probability density. Probability for what, though? Well, books have an answer, which is almost not quite true. There's a lot of uncertainty, as it were. Anyway, at that point I was lucky to meet him who should become my supervisor later. He said, "Do the maths and shut up." Gee, thanks for that inspiration, right? Well, at least temporarily, it's exactly what you're supposed to do. Build up experience and take it from there to deeper understanding. With training comes knowledge. With knowledge comes awesomeness. After all, we can build X-ray machines, smartphone screens and whatnot with the help of particle physics. You knew that probably. Here, I can take it up a notch. The most advanced quantum theory with experiments backing it up at this point in time is QED. I'm not even kidding. Quantum electrodynamics combines quantum mechanics with special relativity. If that sentence didn't make sense to you, think parts of Einstein made weirder. As you would suspect, you can represent QED by means of stick figures. They're called Feynman diagrams, and they're just that, stick figures. Modern physics in one sentence. Mighty stick figures I sacrifice at your altar. At any rate, the only alternative to those stick figures really is a sort of one equation to rule them all. And you can find both Feynman diagrams as well as the standard model equation online, about as easily as images of apples falling on Newton's head. And if you do search and find, you more likely than not end up asking yourself how in the world humans deal with stuff like this. The answer lies in symmetries, that is, physical or mathematical features of a system, observed or intrinsic, which remain unchanged under some transformation of the system. Here's about as much as I can write about that. Equations like the standard model equation describe physical systems. If a physical quantity, something, anything really, stays the same under a given set of cases, we may call it a symmetry for the given set of cases within a given physical system. If you remember your school physics, then the total energy would be a symmetry for the given set of school physics cases. When that isn't quite what you observe, the symmetry is broken and you have to dig a little deeper. And that is a piece for another day. When confronted with an insane equation, we look for symmetries within the framework of the physical reality the equation describes. Using these, we can normally assume weird stuff, which makes the equation easier to handle, and we find out things like this. Atoms are made of quarks. We predict, we prove. End of a usually rather long story. Don't arrest me on the word equation, by the way. I'm too lazy to say nonlinear system of oodles of coupled partial differential equations, which is what nature mostly requires and what that standard model equation really is. No, I'll happily call it an equation. It's enough that I hid in the closet crying for a week or two when first confronted with QED. You don't have to relive that part. It wasn't pretty, but I plowed on. Stuff that isn't made of quarks is called leptons. Those are electrons and a host of other point particles, that is, we safely assume them to not have any physical extension. Good. Now what in the world would a point particle even be, and point as opposed to what? You know, like I said a minute ago, the only spatial extension in atoms and things that make any sense are space-related probabilities. Emity Rutherfordian atoms and all that. Pointing out that point particles are to be treated like points seems pointless. It isn't. And yes, I have stopped crying since. Anyway, it turns out that quarks and leptons make up matter. They interact by means of those 4 forces of nature, each of which has a so-called gauge boson connected to them. Gauge bosons are imaginary particles existing only for the shortest of times. The one for gravity, the graviton, needs a couple of extra spatial dimensions to be feasible as an idea, much less existing. Yes, I just said that. Perhaps I have started crying again too, and stopped again. There's no point, you know. Either you're a physicist or you aren't. I'm a physicist. Simple as that. Speaking about those forces of nature, they're quite the bunch. They listen to names like weak and strong force as well as electromagnetic and gravitational force. We know a bit about the first three by means of a wonderfully absurd structure called quantum physics, of which particle physics is an aspect. General relativity deals with the fourth one. You can read all about them for yourself, but what struck my fancy as a student was just how desperate experimentalists seemed to want to get to high enough energies to test the idea of uniting the forces. See, we know that at high enough energies, say towards the beginning of the universe, the weak and electromagnetic forces essentially are the same thing. There are strong indications that at even higher energies, the electro-weak magnetic force, or whatever it is called, will unify with the strong force, and then eventually we would talk about gravity as well. I will happily admit that my studies drifted into other things at this point. I was still doing physics and still staying interested, but you know, there was a threshold over which I didn't want to go. My specialization would become atmosphere physics, more or less because particle physics had made me cry and rejoice at the same time. There may be hardier people than me out there, and there are, but I couldn't continue with it. I mean, do you have any idea just how much more advanced theory is compared to experimentation in particle physics? No? Well, let's talk about just how we experiment on things like this, shall we? What does it really mean to reach higher energies? Well, the way we try to experiment on the weird ideas of particle physics is by means of some of the greatest machines ever built. Of course, I talk about particle accelerators. These are basically super long tubes. We smash protons against each other inside them at different speeds. In terms of energy, we do get rather close to the Big Bang even. We were able to create the Higgs boson after all, for example. So now you know that too. The problem is we don't get close enough. Thus, we can only test whether the weak and electromagnetic forces belong together, and they do. That's about it. I'd be stupid not to think that we won't find better ways in the future, but at the moment, that's it. That's what we can test. Not to be deterred by this reality, there's a bunch of idealists pursuing the ultimate knowledge by means of pure mathematics. Make the maths work, and you'll likely find out how nature works, is the reasoning. Thus, string theories and humans being flatlanders. Not that I expect that you would have, but if you ever wondered how something can be both admirable and masturbatory at the same time, the original string theory and its derivatives are it. Honestly, in 1,000 years, string theorists may be heralded like we do the likes of Einstein and Newton today. Visionaries who lived well before the time was ripe for their ideas. As it is, I'm not even sure that there are any testable predictions connected to the string theories. Truth be told, the term mathematical masturbation does resonate in my mind here. For one thing, 11 dimensions of space-time are required. Chew on that, as they say in Norway. The point is this: physics is weird, then it's all weird. The New York City sewer system or the blueprints to a car engine aren't exactly intuitive either. Nevertheless, they work to varying degrees of efficacy. The efficacy of physics in underpinning and constructing a foundation onto which we build and develop isn't low. It starts with basic research of nature and ends in X-ray machines at your local dentist. I for one revel in the wonders of nature per se. But for many of my students, it's what humans have been able to extract from the laws describing nature that keeps them going. Modern medicine prolongs life to a point which must seem incredible to people from even only a century ago. We are close enough to understanding the universe for many of the most well-trained scientists in the world to pursue what may very well end up being a pipe dream in searching for the theory of everything. Still, most of the actual work, you understand, is tedious, dull, and not in itself inspiring. Rather, it deals with running against the same walls repeatedly, not knowing whether a breakthrough awaits or not. When the going gets tough, you need something to keep you going. I won't speak for others, of course, but to me it is this. It ain't intuitive, it's weird, it's impossible for me to stop learning. See, I've grown into and out of academia, but never out of curiosity and a childish glee for discovery. So yes, I suck at maths. I was told that I didn't fit with physicists. Was it really any wonder that I got myself that science PhD? No, I don't think so either. If anything, science has, difficult, tedious, and yes, weird as it can be, opened my eyes to the joy of learning. And that, strangely, has led me down a rather remarkable professional path in life. If you want to, search for the terms science, leadership, empathy, and story next to my name and see what comes up. Being kind sometimes means to tell the inconvenient truth. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. Asleep or not, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. The inconvenient truth? Well, physics is crazy. Period. It just is. And that's okay. We can say it out loud. Actually, it's awesome. Listen to that piece about me not being a genius. I love physics because it's crazy. That's crazy. For example, we are quite literally stardust. That's inspirational, right? It's one of the, let's say it's an idea which arises out of the way stars form, radiate their light, and eventually disappear. What they call the life cycle of stars, quote unquote. Part of it all, an important part too, is what's called nucleosynthesis, or the creation of new atomic nuclei in the stars. Now, in order to fuse atoms into other heavier ones, you need temperatures which are higher than we can imagine. The process only happens under extreme circumstances. In the Sun, we get hydrogen fusing into helium. If the star is heavier, say around 8 to 10 times heavier than the Sun, elements such as oxygen, neon and magnesium can be created too. We're talking reactions that require several hundreds of millions of degrees. It doesn't matter anymore whether it's Celsius or Fahrenheit or whatever. In science we use Kelvin. That's Celsius, but actually starting at 0, not at minus 271 point something. There's also silicon fusion. Silicon and sulfur turn into iron, though by means that are a little different and involve hundreds of different reactions, thus creating all the other elements up to iron as well. So we have solar fusion, we have heavier star fusion, we have silicon fusion, which also happens in heavier stars. We get iron itself and all elements lighter than it out of these reactions. Okay, but you may point out that iron is not the heaviest chemical element we know of. What now? Think about it like this. Fusion reactions are one of our attempts to create on Earth the energy source of the stars. It takes a lot of energy to start a fusion reaction, But once it has started, it releases energy. That's been true for all fusion reactions mentioned before. It's what makes the sun shine, as close to literally as it gets. But from iron and onto heavier elements, it'll take energy to start the fusion, and it'll keep costing you as the reaction continues. Thus, the core of heavier and older stars is made of iron. But that's the thing. Once iron assembles in the core of such a heavy star, the radiation outwards becomes less and less, and that's not really a good thing for the star. Well, good and good. It's bringing it nearer the end of its existence, to put it like that. Well, no, that's not true either. It rather kind of changes in a way that reminds science communicators of death. Anyway, what I'm saying is, gravity doesn't disappear. Radiation pressure does. The star implodes first, then explodes into a supernova. And there you'll get the conditions just right to create even heavier stuff than iron. Well, there, and in what's called shell burning. There's also something called the asymptotic giant branch in star classification, but I can't even. Read for yourself if you must, and as I have done, because it's cool stuff, but be careful. Once you dive deeper into it, you'll find sentences like, "Stars are factories whose main business, quote-unquote, is either this or that. Stars have a life cycle, quote-unquote, after all. They're living things with a purpose, and sometimes it seems a consciousness even." If I was allowed to call it my job to study stars, I'd talk about them like that too, so it's not that. It's just, be careful dipping into this subject, okay? Besides, trash cans and the trash inside them are stardust too. Of course they are. We've got more hydrogen in us than metal or plastic trash cans do. And hydrogen is not created in stars. So perhaps they are stardust even more than we. That's crazy. I mean, think of science and history. How did science come about? Whenever we think of putting a number like, for instance, for 6,000 years, quote-unquote, onto the history of science, we need to remember, as it were, the circumstances in which whatever science was back then existed. Who had access to those star charts, for example, which we cite as proof for astronomy being such an old discipline? It was exclusive knowledge, and it was treated as such. It filtered down to the common man, if at all, via a high priest or someone who could very well be a sort of high priest, like a pharaoh in Egypt whose kingship incorporated parts of a high priest's role. We're talking religion and, in fact, power plays. Sorry, there's no way around putting it like that either. Still, with time, measurements were made and discussed. Within the Western world, the Hellenics started doing that. What is a unit of length? Find an answer and off we go. In India, Arabia and China, people were doing stuff like this before, but what separated the Hellenics was how they treated the knowledge they acquired. No kings involved, basically, mostly. They got the ball rolling, underline. See, what these discussions eventually led to was physics, that is, the attempt to describe nature by means of mathematical equations. Kepler, Newton, and all their contemporaries. What did they really do, if not put formulas into everything they knew? Planetary motion, falling apples, and everything else. A mechanical universe, quote-unquote, as Newton saw it. That's the thing with us people, though. It's not enough to know how that apple falls onto our head, or even just realizing why the moon doesn't. No, we have to push further. We have to see where our limits are. And whether you like math yourself or not, it's a powerful tool for that kind of push. In other words, using it to explore increasingly abstract concepts in nature was only a natural thing to do. And thus we have general relativity and quantum physics. General relativity, by the way, is a system of 16 hyperbolic elliptic partial differential equations that we cannot solve, like at all. We use a sort of street fighting mathematics on it. We do that with everything else in modern physics too. We have to. It's the sort of thing pure mathematicians hate. One of them, a friend of mine, puts it like this, and I quote, "Physicists mug mathematics," quote end. Not that I disagree. We wrestle knowledge out of nature. How surprising is it really that we don't understand that stuff anymore? Planck length or galaxy cluster movement. You tell me that you understand it and I call you a liar. Well, no, not directly, but I will imply it strongly. You know, kindness through knowledge and inconvenient truths and all that. What did you say? The idea of mugging equations was kind of funny? Maybe. To me, it's just crazy. It's crazy, but it worked often enough. With quantum physics, we even needed to do it in order to explain what we saw in observations and experiments. At university, you may very well be introduced to the respective subject by means of the Stern-Gerlach experiment. And then you will be asked to skip asking why what happens happens, but ask yourself what the consequences of that electron beam splitting up in that magnetic field would be. 8 years later, you may call yourself a doctorate in physics, and you still won't have understood exactly why that experiment made electron spin visible. Here's what the book says, and I paraphrase. See, it's the spin, and the spin is... Insert long explanation here. And it all comes quite neatly out of the Lorentz transformations which we find in nature. Insert another long explanation here, and I'll stop. Because you could start with observations in nature instead of an observation of a controlled experiment, yes. But that doesn't change things now, does it? In that case, too, you ask the question of consequence, not of cause. In other words, you build your theory on nothing. You can simply state that it works, and work it does. Without it, modern life is a pipe dream. All of it. And you have a choice. Either you find this thought scintillating, or you're afraid. Or maybe there's a little bit of both in you. It's awesome for sure, and hopefully if you're a modern scientist it makes you look upon those medieval architects just a tad less haughty. Cause you're used to your equations, aren't you? Like they were to their keystones. Nobody else is though, and well, to be honest, to everyone but you it's just one big chunk of WTF. I mean, to be fair, when calculating stuff, most terms in whatever equation you think about now will not be relevant and you're left with mostly 2 or 3 terms. Maybe sometimes a few more than that. Then again, most of those letters on your paper are so-called tensors, not just numbers. For those who don't know, there's a link down there in the description to what a tensor is. The link tells you what a tensor is. I'll tell you what these letters being tensors means. Even just 2 terms being left may lead to a system of equations you will have to wrestle to the ground like an angry badger. That's what that means. The equations are the badger in that simile, not you. You wrestle the... never mind. At any rate, your best weapons against that badger are symmetries. Symmetries are the stuff that doesn't change during the transformation of a physical system. Well, something happens, and symmetry is what doesn't change during whatever happens. We love symmetries because they mean that we can set something to 0 and take it from there. The total energy is one of those in school physics. The total energy of a system doesn't change. We set its change in time to 0. The universe itself works like this too. It's got a total energy. If that total energy turned out to not be constant over time, then that would be something to ponder for sure. Multiverse and whatnot. To be honest, that's crazy. It would be extraordinary to find out that the universe's total energy isn't constant with time. Actually, I don't know whether we don't know. It's not important to the bigger point of this piece either. Because you know us, we don't stop pushing onwards because of stuff like this. Heard of string theory? If you followed me wherever you listen to or watch this, you certainly have. I won't repeat what it is, just know that people who are good at street fighting mathematics use their street fighting mathematics to make equations bend to their will and give us one or more theories of everything. Only nothing about these theories, quote unquote, can be tested. So there's that. They're not theories, but that's a, different story. Others claim to have found references to an earlier universe in what's called cosmic background radiation. The way we look at it now, both space and time began at the Big Bang. Both time and space are intrinsic parts of our universe. Think of the 3 dimensions. Time belongs to the universe in the same way. How can anything be earlier then? Any other universe would have its own time. Now, I'm not going to be like Ernst Mach, who didn't believe in atoms because he couldn't see or touch them, so who knows, and this is indubitably true, as of today, these ideas are exotic, to say the least. Talking to string theorists and multiverse people, I get the hunch that they know this very well too. But there is also the enthusiasm that comes with taking an idea and running with it much too far. At the very least, the motivation for it radiates out from the right place, so I'm not even mad at anybody. And if those guys can get their research financed, then good for them, I say. To be honest, I'd love to be wrong about what they do too, even though there was one person telling me that nobody, quote unquote, believes that when I say it. Anyway, we don't have to go into all the fancy schmancy stuff. Think about a square. That's a 2-dimensional geometric object with 4 corners and equally long edges. Now enter the 3rd dimension and you get 8 corners and a few more edges, but you still know exactly what it's going to be, a cube. Now enter the 4th dimension, only you can't, and still we can give the geometric object a name, tesseract or hypercube. We can calculate everything about it too. But do you know what it looks like? Tell me yes, and I'll call you a liar. Well, no, but I'll strongly imply it. Kindness through knowledge and inconvenient truths and all that. And most of all, that's geometry, not physics, right? Wrong. Well, no, it isn't really, but yes, it kinda is. Hear me out. In the 1800s, there was a Swiss polymath called Leonhard Euler who thought it would be a neat idea to express systems of equations in the form of matrices. Along came the physicists of the early 1900s and realized how nice this idea was and how it could be used to note down what is called tensors. There's that word again. You could express long-winded equations easily and, well, beautifully. A couple of letters here and there, that's it. Hide all that nasty badger-fighting stuff, right? We like things that are beautiful, don't we? So we explored what we could do with this shiny tool. Modern physics, that's what we could do. There is a case to be made that without matrix calculations we would not have general relativity or quantum physics. Why? Because the tool, in this case, gave us a way to deal with all the stuff that cannot be imagined. Like we're in a dark room, we don't know how the cake was made or how it even looks, but we stumble into it. Well, not into it, because then we couldn't. Well, anyway, we found the cake and started eating it. Because we could. Think about it. That's crazy. The worst thing about all of this is that we shy away from teaching the craziness properly in school. We need to do it. It's fundamental to dealing with the world around us. And to boot, I just think that the craziness of it all is awesome and not torture to learn about. I also know that I'm not alone in thinking that. Have you ever looked through an oddly shaped piece of glass? We've all done that in school at least. We looked through prisms there, didn't we? And we said, cool, at the colors and moved on. Colors. Think about colors. Most of them you can't see, but our instruments can. In fact, we can receive light with our instruments and split it up into its colors. There are no jumps in the spectrum of colors either. The difference between blue and red is what our brain does to the whole thing. Nature doesn't think like that, and why should she? The colors are all there, pretty much per definition, and we can see them all with the help of eyes and instruments. The key word is spectroscopy. Without it, we wouldn't know the universe. See, it turns out that different chemical elements react to light in different ways. In fact, they react in rather distinct ways, such that we can use light to distinguish the elements from each other. For example, when looking at sunlight with the help of spectrometers, we find that yes, it's white light, but also that there are a few colors which we see less of than expected. Combine this with other measurements and realize that some of those colors get absorbed by the chemical elements in the air, in our own atmosphere. Thus, we can learn about the Earth's atmosphere like that. The kicker with that sort of thing is that it works just as well when we put that spectrometer at the end of a telescope and point it at a distant star. Stars do that sort of thing to their own light too, or they may even create a particular color en masse, and we see that in the spectrum. And all these colors are connected to certain elements, such that we can estimate there to be 74% hydrogen, 24% helium, 1% oxygen, 0.5% carbon, and a little bit more than 0.1% neon in the Milky Way. Yeah, we know this due to colors and the way we look at them. If you're wondering, we can't estimate these percentages for the whole universe for quite a few reasons, but mainly because we don't know how big that universe of ours really is. Anyway, here we sit inside of the Milky Way, telling ourselves that it is a barred spiral galaxy of 100,000 to 120,000 light years in diameter and consisting of 400 billion stars. Okay, that last one is a matter of counting, you may say. Please do count to 400 billion. I'll wait, or wait, I won't, because you won't get there before you die. I'll live my life while you follow your passion, if that's quite okay for you. And that first one? How can we know what the Milky Way looks from the outside while sitting inside? I mean, that's crazy. How do we know that the Milky Way is a barred spiral galaxy of 100,000 to 120,000 light years in diameter and consisting of 400 billion stars? Let's start with that last claim. To count the number of stars in the night sky that are visible to the naked eye, you will use a small cardboard tube. The center tube of a roll of toilet paper is ideal. On a clear, dark, moonless night, hold the tube up to your eye. Then count and record the number of stars that you can see through the tube. That's a quote from a page I'll link to below. The professional version isn't that different. Most super telescopes have a rather narrow field of view, quote unquote. Make it even more narrow artificially and follow the process. Then scale that up to whatever piece of sky you're interested in. Such, we know how many stars there are in the Milky Way. We can also track the movements of stars by spectroscopy and colors, and how they are shifted away from what we would expect. Then we do geometry in our heads, or on pieces of paper, or with the help of supercomputers, and conclude after a while that we live inside a so-called barred spiral galaxy. Aren't we the clever species, huh? To interject quickly, the history itself is a little bit more complicated than that, and involves realizing that there was such a thing as a galaxy in the first place. For most of science history, we considered the Milky Way to be the universe, period. In terms of school physics, this is, of course I might add, not really easy to discuss. Sure, we can repeat all the talking points from TV, all that big banging and universe expanding told in front of either a starlight or a sunlight shot. I won't though, I just want to appreciate for a second just how intriguing these things are to especially kids, and how difficult it is to talk about them properly, that is, without dumbing down and still communicating its awesomeness. We guess sophisticatedly about nature, and have the endurance and interest to follow any old weird line of thought. We have historically been awesome at following any old weird line of thought. That's it. Being kind sometimes means to tell the inconvenient truth, because that's it. Nature's complex, so it takes thousands of weird ideas to get to that one idea which works. But science isn't complex. Science is just coming up with those weird ideas. Well, within boundaries, of course. You can ask questions and take a guess. But if you don't know how you would check whether you're right, then you can just forget it. That's the only limit though, the only limit. Just take energy. The total energy is the stereotypical example of a symmetry. It doesn't change, never does in a physical system, yet you don't know what it is, even though you may think that you do know what it is. You really don't, because you can't. It's like flying. You simply can't unless you use a plane or some such contraption. Energy is nothing you can understand unless you use math or experiments or some such thing to gain experience with it. Physicists do just that. Mostly they do just that and get all giddy when a proposed symmetry is broken. That is, it's not holding. That in itself is crazy too, and you know that's okay. Physics is crazy. It's a discipline that hops from one thing to the other incrementally, but still in ways that are impossible to predict. It has to be like that too. It is, after all, the science of stuff we have no right to know. In fact, one may argue that it is the science of stuff we are not even in a position to really ever know. I mean, honestly, what is gravitation, for example? It's a theory, okay? It's got to do with stuff falling down, but what is it? What makes stuff fall down? I don't know. Do you? And isn't it crazy that we don't? Dreaming the Science Way. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. Asleep or not, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. We'll start by going back to the Roaring Twenties, or whatever that time between the wars was called. Towards the end of it, there was a man who got himself access to the largest telescope of his time, and he used that access to make observations. The man was Edwin Hubble, he of the latest space telescope. The observations I'm thinking of were of 23 objects in the sky. The measurements were made of the distances of these objects and what is called their recession speed. That is, the speed with which the objects recede from Earth. Within the boundaries of statistical analysis, all objects had a respective speed that followed the same line in a plot in which the speed axis is logarithmic. Forget all that. It just means that these 23 objects in the sky move away from us. And that's not what we would have expected them to do. At that time, astronomers assumed the universe to be static in time and in space. The idea was established in an actual theory, the steady state theory. A theory in science is the Holy Grail. Gravitation, for example, is a theory. Now, imagine someone coming along telling you that gravitation is wrong, that Apple should fly and does so, in fact, when it's not you, but me looking 23 times. That's what Hubble did and said, really. He had exclusive access to the largest telescope in the world and could see things others couldn't. So he went to his colleagues, some of whom envied him for this access, and told them that their theory was wrong, based on only, again, 23 observations. Because that's another thing. 23 observations is, as it were, next to nothing. Of course, if that kid on the football field made 23 out of 25 free kicks, for example, you'd rightfully think that she's good at free kicks, but if somebody came up to you claiming that she was the new female Messi or Beckham, depending on which generation you belong to, based on that one performance, you'd be slightly careful about it, right? Hubble's colleagues were slightly careful too. They dismissed his ideas. It's one thing to have made these 23 measurements, but quite another to challenge the theory of the day based on it. So why isn't a static universe the theory of the day anymore? Why have we replaced it with the Big Bang Theory? Well, I'm sure there's going to be episodes on this in the future, but I can summarize the idea here too. Whatever we can test about the Big Bang Theory, we have tested. and it worked about as well as it could, and in significantly more than 23 cases. Yes, there are alternative ideas out there like modified Newtonian dynamics and some others, but they have that one problem the Big Bang Theory hasn't. Some of their testable predictions were disproven by observation and experiment. That's it. There's nothing more to say from the perspective of the everyday person. The Big Bang Theory is about as true as the word true implies. What about black holes then? There's an image of one out there, so it should be simple to proclaim their existence and leave it at that, but it isn't quite. Hear me out. According to Wikipedia, a black hole is, quote, a region of space-time where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it. Quote end. A region of space-time. Alright, space-time is worth pondering all by itself, and I'm sure we'll do that too at one point. Not now though, because, how do you prove the existence of something like black holes? And is that really an image of a black hole there on Wikipedia? Truth be told, astrophysicists also struggled with this for quite a while. The evidence for the black hole's existence is based on the effects of gravity. The stars around the center of our galaxy, for example, move in a way that cannot be explained without there being an object in the center, which we would be able to categorize as a black hole. There are also the gravitational waves we have found after a merger of two such stars. You get the drift. We see its effects, but we can't see the black hole itself. In other words, we know it has to be there, but we can't see it. Wait a second. Black holes are stars? What is a star? Now here's a question you've never asked yourself, and the detour will be well worth it, I promise. A star is a heavenly object which has accrued so much matter that fusion reactions happen in its center, where the material is densest. Let's see. There's two forces. Gravity, which draws stuff together to a point where and when nuclear fusion can take place. The energy released during the fusion reaction needs to go somewhere, but there isn't really anywhere to go. For in order for this reaction to start, the atoms need to be tightly packed. In order for them to be tightly packed, there needs to be a lot of stuff around them. In the Sun, for example, nuclear fusion only happens in the very center, with several hundreds of thousands of kilometers or miles, whatever, worth of matter on top of it. So the energy released in the nuclear fusion reaction wants to go somewhere but can't. It pushes back against gravity and does so as much as it can. There's a balance in the end which gives the star its size. Gravity inwards, radiation pressure outwards. That's how it is. Unless something else pushes back against gravity, stuff like quantum degeneracy pressure of different kinds, and no, you don't need to look that up right now. It's complicated and changes nothing about the underlying idea of two forces. Now, these two forces and their balance determine everything. Everything you've ever heard about stars, from how they form, what they are, and how they die, all of it. See, if gravity is rather strong, the star is rather massive, obviously. There's a threshold there, I think it's 25 times the sun's mass or something like that, above which the star will end up having a chance to become a black hole. On the way there, they have to blow up twice and create heavy elements like iron and things like that. It's all quite awesome and worth exploring. With respect to this piece, it's sufficient to say that only the very largest stars, in which this balance is skewed towards gravity about as much as it can be, become black holes. So let's go to that famous image. As mentioned, you can find it connected to the black hole article on Wikipedia, with a little explanation too. It's going nowhere and it'll stay famous for a while, so it'll be easy to find at your leisure. The point is, black holes were once a weird idea, and people didn't like this idea when it first came up, hence the name black hole. It's the same story as with the Big Bang really, but black holes like the Big Bang aren't weird anymore. At all, for we have made the invisible visible by first observing its effects and then making it appear in what artists call negative space. Awesome, isn't it? By the way, we've always been observing effects. Take atoms, for example. The idea is old, like really old. A guy called Democritus and some other Hellenic philosophers had the idea of unbreakable smallest things in this world, which would create and be nature. That's not bad for a guy who laughed at the folly of his colleagues while proposing invisible, indeed invincible thingies to float around and make up everything. Don't make that dad joke now, please. Anyway, the truth, if we can use that word, turned out to be, well, not less weird, arguably weirder. There's Dalton's atomic theory and Thomson's plum pudding. Not kidding. But when Rutherford came in, things turned strange. Rutherford. That's the guy who didn't conduct his famous experiment, but suggested it to two folks called Geiger and Marsden. You can, if you wish to do so, look up the details of the experiment, but here's the gist of it. They shot so-called alpha particles, that is, helium without the electrons, onto a thin sheet of gold, and then tried to measure behind the sheet whether some of the particles got through. There's more to the setup, but for our purposes the word is yes, they got through, a great many of them, like 98 to 99% of them. To you and me, who have gotten used to this being the case via school physics and school chemistry, it's all good. But for the scientists of the 19th century, it wasn't good at all. They believed in the plum pudding and found now that the plum pudding wasn't a good idea. In fact, and here Rutherford actually comes in, they, Rutherford that is, explained the experimental results by means of atomic nuclei, which needed to be excruciatingly focused centers of mass. Atoms are, in a physical sense, mostly empty. Now, to chemists, the existence of atoms is nothing new, but physicists got interested too, after this, and boy did they get interested. We'll take a tour to Vienna, around the turn of the 19th to the 20th century. We'll talk about Ernst Mach, he of the Mach number in aerodynamics, and Ludwig Boltzmann, he of the Boltzmann constant in thermodynamics. One knew a little chemistry and thus about atoms. The other we would call an engineer today. That last one was Mach, obviously, if you think about it. And he didn't believe in anything he couldn't touch or see. He derided the very idea of an atom and drove Boltzmann into suicide by attempting to destroy the younger man's career and life. Now, that's an urban myth, not the suicide, but the reason for it, and I will not tell you that it's true. It quite probably isn't, or at the very least it's much more complicated than that. I don't know. Still, the existence of empty atoms was difficult to accept for many. Rutherford be damned. In fact, it was so weird and out there that a special experiment had to be built to get the Machs of the world to just be quiet, as Aunt Agatha would put it. Plum? Anyone? Shout out if you got that reference. The experiment which settled the debate was Wilson's cloud chamber. I don't know why this experiment was better to show the existence of atoms than Rutherford's or any of the other ones was. After all, the Geiger in Marsden is he of the counter, which, you know, literally counts particles. Perhaps it's the way alpha particles were made visible. Maybe it's the connection to cosmic radiation that was to come. But Wilson did get a Nobel Prize for this. At any rate, atoms. Here they are, such as they are. And here we are, such as we are. Atoms are. They exist. What does that mean? I mean, like atoms exist, quote unquote. What do we mean by that? Really? I don't know. Sorry, but I really don't. Usually, if you ask physicists stuff like that, they either talk about quantum physics, an aspect of it like particle physics, or some out there ideas, which develop from the maths in quite the obvious way. That doesn't help though, because quantum physics is really just an elaborate model to describe microscopic nature. It's a description, not reality itself. So, quantum physics. Now here's something fitting perfectly into this piece. Remember, we're talking about ideas that were weird at the time of discovery or development, though we are still at ideas which turned out to be okay. And I'll quote Wikipedia on it. Quote, "Quantum physics gradually arose from theories to explain observations which could not be reconciled with classical physics, such as Max Planck's solution in 1900, to the blackbody radiation problem, and from the correspondence between energy and frequency in Albert Einstein's 1905 paper, which explained the photoelectric effect. Early quantum theory was profoundly reconceived in the mid-1920s by Erwin Schrödinger, Werner Heisenberg, Max Born, and others. The modern theory is formulated in various specially developed mathematical formalisms. In one of them, a mathematical function, the wave function, provides information about the probability amplitude of position, momentum, and other physical properties of a particle. Quote end. I hope you noticed the word gradually. That's the science way, step by step like, explaining an observation here, testing an idea there, and then at the end you have this grand thing which powers our modern civilization a century later. However, quantum physics is the house without a foundation. It's the craziest idea of them all. You can assume that a particular mathematical transformation has physical significance, say, for example, in such a way that it will make velocity out of position or turn energy into time, physics-wise. If you assume this in the right way, then you have just formulated Heisenberg's uncertainty principles. From there, you can build up all of quantum physics and with it explain experiments and do everything. Yet, you'd still be in a position where you haven't explained the assumption to start with. Is there any good reason for you to make it? Well, let's say they haven't come up with a good reason yet. And you can do this the other way around too. In my very first quantum physics lecture at uni, the professor told us a variation of the following. In this experiment we shall not ask what happens, we shall rather ask about the consequences of it happening. That's a big one. I spend a lot of time telling you that science is about finding the right questions and then answering these questions. Finding explanations for stuff that happens is what scientists do, right? Right? Well, yes, they do. But there are openings for other stuff as well. There's nothing wrong with asking about the consequences of something being the way it is. I mean, why should a good question always be about why stuff happens? In fact, quantum physicists have, basically from the start, been divided into two groups. Those who asked about the consequences of that experiment, or others like it, and those who wanted to know why it gave the results it did. The former ones led the charge to build the theory and ended up explaining why those mathematical transformations from just a minute ago make sense, physics-wise. The others still argue about multiverses and other so-called interpretations of quantum theory. The experiment? The Stern-Gerlach experiment. It's wonderfully absurd. It introduces the concept of quantum spin and even made a substantial number of scientists go F it. I don't even want to know. Let's just take it for granted and go from there. I don't think that had ever happened before then and hasn't happened since, to my knowledge. Please tell me if I'm overlooking something obvious. But yeah, quantum physics may be the foundation of modern society, but it itself has no foundation we know of. To put it bluntly, we have no right to even know about it. And yet here we are. We're awesome. Of course, it's difficult to talk about it all to people who aren't scientists. And why would it be easy? Even a physicist who claims he understands quantum physics is simply wrong about his own ability to grasp stuff. Enter Clarke's third law. Sufficiently advanced technology is indistinguishable from magic. We could probably rewrite that as any technology, no matter how primitive, is magic to those who don't understand it. Yes, I'm thinking about flat earthers now. Yet not only about them, I think about us. People invest in thoughts or have their parents invest in thoughts for them. It's a daily thing. We all do it in one way or another. I mean, there's a reason customs, that is, the ways we've always done things around here, change only slowly. I had a boss, for example, who thought my biggest talent was to manage projects, and not even the reality of a decade of feedback from those I've taught could prevent him from taking me out of the classroom. Now, to be sure, I do enjoy managing projects. It's my living right now, but I didn't need to do it for a teacher's salary. Expecting me to do so was slightly surreal. And yes, there's a reality about teachers' wages here that warrants a proper re-evaluation of the whole kindness through knowledge idea. If there's one thing to get angry about, then But for all the things he might have been, a flat earther, my former boss wasn't, and hopefully still isn't. Anyway, what I'm talking about has always happened to scientists too, and even their predecessors. Don't believe me? Well, did you know that many Hellenic philosophers said, what is beautiful has to be true, and went from there to explain the universe. We still do it. Ask any string theorist about string theory, for example. It's another one of those ideas that seem too weird to be true. You know, like the Big Bang Theory, black holes, atoms, or quantum physics. String theory. Well, we can start by being a little pedantic. It's not a theory. Gravitation is a theory. String stuff isn't. Just to get that out of the way. What's string stuff then? Imagine the 3 dimensions, up, down, sideways, and back to front. How would you fit other dimensions into that? Because that's the thing about string stuff. You put another 7 dimensions in there and boom, you can explain everything. Quantum theory and gravitation combined? No problem. Everything is everything. Okay, I'll dial the tone back now. In fact, I apologize because string stuff people know what science is very well. You know, they imagine so-called localized dimensions, invisible to us, but very existing, and use these to think of strings of energy vibrating within these dimensions. I don't, to be clear, but depending on the kind of vibration, the different particles of particle physics and, as an extension, our macroscopic world would come to be. Strangely, it all works out mathematically. By the way, the word imagine is not false here. What's a hypothesis other than a sophisticated piece of imagination? Again, those guys tend to know science. I've heard string stuff being called not even wrong, and I can't say I disagree. There's nothing about it that can be tested in any way, shape, or form. Yet I can't help myself but understand it all too. String stuff is beautiful and elegant, so much so that something rings true about it. And as those Hellenic philosophers said, what is beautiful has to be true. In addition, a lot of the string stuff people are really, and I mean really good at the kind of maths required in physics. And if you're good at it, then you love doing it, and then, well, hammers and problems being nails and all that. In short, I get it. I really do. Still, string theory isn't a theory. It's not even wrong. Period. Sorry. What about engineers? They don't do stuff like that. They can't be doing stuff like that. Well, there's something called the M drive. So yeah, they do it too. Imagine a metal cavity, a beholder of some sort with, say, the basic shape of a cylinder, for example. Now make one of these 2 base areas of your cylinder bigger than the other one and bounce microwaves around the beholder. The idea is then that the radiation pressure is different on both sides of that cylinder, thus resulting in a net force on one side of the beholder and accelerating the whole thing and anything connected to it. It's a question of physical systems and how forces in fact work. See whether you can spot the flaw. It shouldn't work now, should it? Yet here we are. I could, if you wanted to, refer you to a peer-reviewed and published paper describing measurements that should give you pause, at least until you remember what scientific papers are really supposed to do. They are there to throw ideas at the proverbial wall to see whether they may stick. And yes, I could get into more details of how this is supposed to work. I won't, because there's nothing to understand really. And I'm not going to put people down just for the sake of it, like, you know, wallowing in very fundamental physics and pointing out stuff here and there. Truth be told, I wouldn't really make a point of that either, but that's the world we live in. I just hope you believe my good intentions. You'll see what I mean in a second anyway. The paper itself is rather cautious, to be quite frank, and simply reports on an experiment with some results that warrant further investigation in the eyes of the researchers. In addition, the team of engineers responsible for the paper are from Eaglework, a laboratory which is loosely tied to NASA and has its goals precisely in investigating what they call fringe technologies. That is, stuff which shouldn't, but perhaps with a little luck might work. It's a tradition in American engineering to have people for stuff like this. Nikola Tesla was this to Edison when the Serbian worked for the American. If you've ever heard of DARPA, yeah, they're like that too, just in terms of how to best kill people, of course. Yet here's how the M-Drive paper got picked up on, for example, Science Alert. It's official! NASA's peer-reviewed M-Drive paper has finally been published. That's technically true, but implying so much more, right? The Holy Grail published. Well, granted, it's more than we usually get, but not enough by a long shot. And I'm sorry to single out one blog, one post, and with it one writer like that. They've got other stuff too, so yes, please do go and check them out. But that post is just too representative of how the M drive gets picked up every once in a while. I mean, researchers talk to journalists, get sublime feedback on their own ideas in this way, and make them as interesting as possible, usually without even knowing. I've certainly fallen into that trap a couple of times myself. Another part of it may be that you are faced with rather strong counter-arguments, which, when combined with the fact that you have spent a lot of time on your idea, might just be too hard to swallow. The journalist, on the other hand, is usually quite excited about things like this. Science and technology fans, I'd venture to guess that most journalists would absolutely and utterly love to live through times of developments such as the M drive, as do I. In other words, I understand the researchers, I understand the journalists, but that still doesn't make the idea right. I mean, who cares about the measurements having been explained by engine eating afterwards? In this way, I'm not even sure that the way Rational Wiki treats the subject is quite right. They categorize M-drive literature like this, and I quote, 1. Word salad of the not even wrong variety, as that phrase again. Too vague and ill-defined to generate any actual predictions. This comprises Harold White's quantum vacuum plasma crap, McCulloch's quantized inertia, and other unspecified space magic stuff. 2. Explanations which are sufficiently precise and well specified, but are demonstrably wrong. Here we have Scheuer's original theory or Arthur Anila's Zen rocket. Quote end. Don't get me wrong. You'll find Rational Wiki's writing to be quite truthful, yet the tone in this and many articles on the wiki is, well, let's say somebody takes the bait and enters the realm of argument. That too is completely understandable, but also a bit of a shame. See, at the end of the day, we're humans and we dream, and dreaming is allowed. After all, we've been wrong before. Even though the M-drive is not a true working thing and won't be either, you can't draw yourself up in the air by your own hair, you know. We still shouldn't be looking grimly at it. The Big Bang Theory works. Black holes and atoms exist. We take esoteric ideas and run with them to make practical things basically all the time. It's not just quantum physics either, it's stuff like Euler's matrices, Fourier's transformations of random functions into sine wave sums, and a whole host of other things. So yeah, that string stuff physicist is right. When kids look up to great scientists the way they do to great musicians and actors, civilization will jump to the next level. That was Brian Greene, by the way. What does all of this mean? Who knows? It depends on your situation. You know best, but hopefully I did put some thoughts into your head. So leave a like, share this with other people who commute or should hear it for whatever reason. If you want to share your thoughts, how they arose and which environment they fit, I'd be thrilled, but even if not, dream on and warp speed ahead. Just know that dreams are motivations to do something, not ends in themselves. So, the weather's chaotic, I said. What does that even mean? Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. What's chaos? Think about the word for a while. What is chaos to you? Here's an example from daily life. If you've ever been to a busy town market, you know how people move around each other there. They don't touch each other, much at least, and most of them keep moving. There's bigger people, smaller people, children that is. There may be bicycles or carts or whatever. Everything is moving, but nothing is touching. Looking at it from a bird's eye view, it's chaos. It looks like chaos. This is a chaotic scene. So much so, in fact, that it may raise your pulse to step into it. How do we get through this? Where's the stall at which we were supposed to meet our friends? Are we too late? Have they come? Yet, if you take the time to ponder, you might notice something about it all. You are not moving randomly. You try to find that stall at which you were supposed to meet your friends. You may not have a direction yet, but you have purpose. You do things for a reason. You have cause to do things the way you do. That's true for everybody else too. Well, duh. Of course it is. Everybody is doing something on that market. Okay, keep that thought as we move on to movie mountains. Movie mountains are difficult, or at least they used to be difficult for CGI artists because, well, in order to make them look natural, you had to somehow recreate the mood, the feeling of them. You could try to do the Bob Ross thing on a computer, sure, but then if you did that, you were left with a 2D image, which is no use if, say, a bird flies through the mountains in your movie and you want to follow it and see its view. Think of Gandalf being saved by Gwahir at Orthanc. Look out of Gandalf's eyes and understand that you need to get those mountains right in 3D. The way to do that is by means of so-called fractals. In fact, whenever I meet somebody who has heard of fractals, the first thing they tell me about are fractal landscapes. Movie mountain. That right there, by the way, is an internet search term if ever there was one. Fractal landscapes. So, take for example an equilateral triangle, that is, a triangle whose sides are equal in length. Divide each of its sides into 3 parts. Construct another equilateral triangle on each of the sides, on top of the line segment in the middle of each side. Do this until bored. Now, that process in itself will lead to what is called the Koch snowflake. However, what if you randomly decided to only do it to some triangles? Others will just border triangles of the same size. Or what about moving the connection points slightly, making the smaller triangles just a tad non-equilateral, as it were? Finally, you could also introduce a third dimension into it and start building up shapes in all directions, that is, at random angles of the triangles to each other. Confused? Good, because that's the point. Doing confusing stuff can give you nice and shiny 3-dimensional mountains. It doesn't have to, but if you think in terms of a code and how you would set parameters in that code, then setting the parameters of that code right will give you mountains. Technically, you need different fractal dimensions applied at different scales, quote-unquote, so-called multifractal techniques, to get it very right. And you know, what I have just described is one of the rules of chaos. It's called self-similarity. The structure is similar to itself. Triangles sitting on top of triangles like... But I moved too fast now. What were we talking about? Oh, yes, dimensions. Ponder them for a while. Then I'll blow your mind just a tad more. The way to think of dimensions is by imagining our 3 ones, up, down, left, right, to and fro. Then imagine there not being 3 dimensions, but let's say 2 2/3 of a dimension. Okay, maybe that's no way to imagine anything, and mathematically it isn't quite the right analogy either, but the word dimension is in the lingo. The numbers 2 2/3 for that matter may appear too. So, dimensions. We'll roll back and look at the very concept of a dimension. Think about a point in space. It has no dimensions. Not a point in the way you would draw it, that thing you can look at under a microscope or magnifying glass and have an opinion of the thickness or radius of it, right? No, I'm talking about a mathematical point. No extension at all, thus no dimensions. Can't imagine that? I can't either, but you'll see what I mean in a second. A line would then have 1 dimension, and you can imagine that. Because, say, you draw a line in order to measure something, then you won't be interested in the thickness of the line, usually. You'd be interested in its length. So a dimension would, in this sense, be the part of whatever you draw or build that you would be interested in measuring. A line has 1 dimension. I say build because, of course, you can draw lines in different directions and construct, say, a rectangle. A rectangle has 2 lengths of interest, thus 2 dimensions. But you can't draw a cube, I mean an actual cube or a slab or something like that. You'd have to build a slab, which has 3 dimensions of interest. And here's the kicker. Mathematically, not in your mind, but mathematically, the easiest way to describe quite a bit of nature, from leaves to lightning, would be to give the respective thing not 1, 2, or 3 dimensions, but 2 2/3 or 3/4 or something of that nature, as it were. Forget imagining it properly. Stay with a couple of models, quote-unquote, to work with in order to just get a step further towards understanding. So, imagine a plane. It has 2 dimensions. Then imagine a slab, which has 3 dimensions. A hillside would then be something in between a slab and a plane. It's not a plane, but the third dimension isn't relevant to the same degree everywhere either. The hillside isn't filling out the slab, is what I'm saying. So one large hill would be closer to 2 dimensions than many smaller hills would. Again, it's not intuitive, any of it. But it works. Moving on. And we can just move on because in this way we have described what is called iterative function system fractals, quote unquote. You take some form or other and scale it upwards or downwards. Well, formally there's a lot of talk of transformations, rotations and stuff like that. But we don't need to care about that anymore. Iterative fractals is what we, so far, meant when we used the word fractal. To most people who've heard the term fractal, it is connected to wonderfully beautiful images. These images are basically visualized equations and as such very useful to any science communicator in and of themselves. Beauty of math, beauty of nature, beauty of life and all that. But there are down-to-earth applications to all of it. Think of coastline. You know this most famous example probably. If you were to take a map and measure it out, you would find any coastline to have a certain length, say 5, apples or parsecs or whatever. Now if you take another map, a larger one with a higher resolution, and you measured it again, you'd find the coastline to be 50 apples long. On an even larger map, with an even higher resolution, the coastline is 500 apples long. Okay, I'll stop with the apples. But, that's what happened to surveyors who attempted to measure the coastline of the largest of the British Islands. So it's a real and very fractal thing. I'm a space guy, so of course we're going to look at space stuff too. Stars are born, as they say, in clouds of moving gas. Turns out that gas clouds in space are fractal in nature. Think about the smoke above a candle. The gas moves up and turns in on itself in ever smaller vortices the higher you get. That is, the further you get away from the candle. If you look closely, you'll be able to suppose that these vortices and where they form show self-similarity in the way I described it just a minute ago. Generally, turbulence, that is, the vortices, in any sort of gaseous cloud, behave like this. Knowing that stars form in rotating disks of gas, with loads of turbulence in them, it becomes quite an attractive thought to connect that turbulence to star formation. Remember the piece on the Earth's atmosphere? I don't expect you to remember any of the details, and why would you remember? But one of the things I told you there was how turbulence in a gas distributes whatever is in the gas uniformly and smoothly over the whole volume of turbulence. That is not conducive to the kind of focus of matter we need for stars to form out of the gas. But lumps of matter can induce turbulence and create the sort of environment around them where they feed themselves with ever more matter. They redistribute what's around them by means of turbulence and secure getting fed for as long as there is matter around them. Kind of. I don't know. Star formation's complex and I may very well talk out of my arse here, but it's fun to just let your thoughts go for a second, right? There are also some applications of fractals and the underlying math in biology. You all know about the leaf and its branches, right? Trees too, and where they in fact branch off are another example. Every branch looks like a miniature version of the larger branch it branches off. Branch. Now, did you know that the basic structure of a chromosome is like that too? Every chromosome consists of a mini version of itself. You look at the whole thing in 2.5D. Not even kidding. The fractal dimension of a human chromosome, for example, is a little more than 2.3. There's also DNA, which seems to show fractal substructures. I'm sure the biologists among you know even more examples. In computer graphics too. I mean, the mountains are one thing, if you've heard about fractals. You've heard about the mountains. But there are many more applications, and CGI is still the most common everyday use of fractal geometry, not least among them image compression. In other words, fractals and with them the theory underlying them are beautiful. So, chaos and fractals. How do they belong together? We all talk about them together. They follow each other in science communication efforts like this one, like the two variables of the uncertainty principle. What gives? Well, some chaotic systems have what is called strange attractor orbits, quote-unquote, in what is called phase space, quote-unquote. These are fractal in nature themselves or are of fractional dimension. Thank you. I see myself out. No, I won't, and I hope you stay with me too, because we can move on from here without losing our minds. Imagine a circle drawn on a piece of paper. It will have a center point and everything. It will be just a circle. Have you ever wondered what makes a circle a circle? There's a center point, yes, but what more? There is also the curvature of the line which makes the circle. It is constant, that is to say, the line of the circle always bends exactly the same way, never more, never less, never in any different direction. Imagine now a line which looks like a circle at first glance, but never quite gets there. The curvature keeps and keeps changing no matter what happens, and if you trace out the line, it just never seems to be able to close. If you consume this content on a medium which doesn't allow for imagery, then look up the butterfly effect, quote-unquote. Otherwise, just look on screen. It could be like this. What's weird about this sort of line is that it won't fill out the paper/background uniformly either, if you keep going. If you were to completely randomly put dots on the paper, you'd eventually fill out the paper. Not here. You've painted chaos in the mathematical sense. It's not a nice closed line, but also not a completely filled out paper. It's something in between. It's fractal in character, whatever character in this sense really is. Now, that's still as abstract as it gets. But if you remember this example, then I'll promise you that we'll get there in the end. Here's the next thing to think about. Dynamic systems of fractal nature are driven by some sort of recursion. Whenever recursion is a thing, the initial value of whatever variable is recursive is highly important. That means a small change in that initial value can lead to vastly different outcomes. Programmers know this. And that's weird because the lines of the code don't change. We have set the rules of the process, yet still the outcome may be vastly different if we change that one number, and only slightly at that. The line I talked about just a minute ago can look vastly different if you just start at a slightly different place and draw into a slightly different direction. Or another example, go check out the double pendulum at your nearest science center. Follow the outermost point of the double pendulum and keep the speed with which you rotate the thing constant. The orbit traced out by that outermost point will be different every single time you start the process anew. Because two ball bearings in the pendulum mean that its starting position will always be a little bit different from last time. Not so much that you may see the difference, mind you, but that's the point. Small difference in the starting point, huge difference in the outcome. Even if you could really keep that rotation velocity constant, and despite gravity, which is really what determines the movement of the pendulum, not changing at all. That's chaos. A leaf or the structure of lightning when photographed isn't chaos. It's a snapshot in which you may glimpse the fractal nature of it all, but fractal dynamic systems are a type of chaotic system, per definition. The rules are set, but honestly, you can't really predict anything because the sensitivity to the starting point of the process is just that big. Weather's chaotic too. Ever wondered why? Well, I could again send you over to that piece on the Earth's atmosphere that I've put out a while ago, but here's the short answer as to why. The sun shines on Earth. Earth warms up and sends out its warmth in the form of infrared radiation. The infrared radiation heats everything close to the surface. There's a lot of air and atmosphere close to the surface. We like that because it gives us an environment to live in. But we sometimes hate it too because, well, weather happens there, with all that entails. The whole thing is called the troposphere, and everything that happens in it is dependent and indeed dominated by the infrared radiation sent out by Earth. Closest to the surface, there's a lot more turbulence than you think. But then, weathermen can't predict the weather 100% now, can they? See, and they can't, because the physical system in which weather happens is a dynamical, chaotic system. The starting point for, say, building up a cloud in the sky will always be just a tad different from last time a cloud built up. The cloud will then look very different from last time and thus create a quite different environment around it, including winds and stuff like that. Things simply will be different, though the initial process of creating that first water droplet in the sky is almost the same as last time. Almost. And this isn't even the whole story either. I mean, Have you ever wondered about what clouds really are? How and why do these little droplets or ice crystals float up there? How do they move and stay together? Well, that's one big story which will warrant its own telling at one point. But for now, I just want you to realize that clouds aren't boring, like at all. They, like everything else in the Earth's atmosphere, contribute to how energy flows around, gets absorbed, sent out, reflected, and everything. It's one big mess of sometimes more, sometimes less beautiful physical, chemical, and biological processes, which can, as we physicists are wont to do, be summarized in one simple expression: energy budget. We always do this because human minds work like this. We put a stamp on something and then allow everybody to dig below the surface as much as they want to and feel comfortable with. Here goes. Level 0. You know what a budget is. Forget money. Think of energy in the Earth's atmosphere instead. Where you are, for instance. It's a certain temperature there. That's the bottom line, the end result. To get there, you can understand level 1. There are processes that make the air around you warmer and some that make it colder. These may be warm or cold winds blowing in. But there's other stuff too. Ever felt how everything gets a little colder when it's rainy or when you are in a fog? That's when sunlight doesn't hit you directly in the face anymore, as it weren't. So the incoming energy on your forehead isn't as big. That has an effect on your budget. You know, stuff like that. You count it all up and get your bottom line. Air, smog, pollen, smoke, and, cloud droplets and all that. Level 2. There's chemistry. Ever heard about the ozone hole? Yeah, that. You're gonna have had a little bit of chemistry in school to understand, but if you have had that, then this is going to be okay for you to think about. It's chemical reactions, some exothermic, some endothermic. And there isn't just ozone, there are nitric oxides, smog that is, which react chemically as well, and a host of other stuff like it. Level 3. This is where we stop understanding anything. See, we can be nice to ourselves and for the purpose of this piece call quantum physics chemistry and put it all in the same pot. Don't kill me. I do this solely because most quantum stuff in the atmosphere is easiest described and understood as chemical reactions. Sorry. And besides, we don't need to go all quantum again to leave the realm of understanding. The air itself is quite sufficient for this. Just looking at how the air moves around you, you will find that there are underlying structures to these movements. Yes, stuff like this wind appears every half year during the dry season, or something of that ilk. But you will struggle to actually predict anything about it. Exact date, exact strength, anything. But by that point, we're no longer surprised, because weather's chaotic, so why would winds not be? And that's the thing. Markets, rivers, clouds, and all the other examples have one thing in common. They adhere to the rules of chaos. Every movement, everything that happens has a cause, yet so much happens at the same time that we wouldn't be able to calculate and predict details of what happens even if we tried to. See, in principle we could. The marketplace, for example, is like a plasma, ionized gas that is, in that there are particles in a plasma that interact with each other at a distance. In a plasma, that is the electromagnetic force. In the marketplace, it's people seeing each other and thus avoiding each other before touching. We could use the same equations, actually, and scientists have done so in their spare time for a laugh. But we can't predict anything of substance because too much happens at the same time. That is chaos. We know the rules and know the causes. When rules and causes disappear, things are random. So, yes, the market is chaotic, but be honest, did you think about it in this particular way? There are no limits to imagination, they say. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. Consider an apple falling from a tree. What presses or draws the apple downwards? Gravity, you say. Well, imagine gravity then. There are many ways to think about gravity. For example, one may consider space itself to be a kind of fabric which is fastened to some structure, such that a body of mass lying on top of it will distort it. Alternatively, what drives gravity may be a particle racing back and forth between the apple and the earth to inform both that they should attract each other. Physics is about facts, isn't it? Many people think exactly that because both ways of explaining gravity have been used so often that it is easy to believe them to be truth instead of describing truth, which in fact they don't actually do very well. For example, think only about how we live in a three-dimensional world, while our piece of fabric is two-dimensional. Thus, we get lost between what we think we know and what we imagine. For it is possible to come up with solutions to all sorts of questions. Imagination is almost without limits after all. Does that mean we should just invent things? Einstein's equations on general relativity, for instance, predict something called gravitational lensing. If there is, say, a galaxy in the way of the light from another galaxy behind it, then there will be smudges of light around the galaxy in the foreground. Depending on the mass distribution of that foreground galaxy, those smudges can be points, banana shapes, yes, banana shapes, or even rings. Now, you may be listening to this piece, not watching it. So you'll just have to believe me that taking up an image, say of the Einstein cross or any other suitable object in the deep sky, makes it quite simple to describe the effect. The foreground galaxy simply bends light around itself. However, we don't just want to describe, do we? We would like to know why things look like they do. We want to know how they work. How can a galaxy bend light around itself? I mean, huh? Consider now a bright kid who thinks a little bit more about the Einstein cross and concludes that this has to be the same phenomenon as when you are up to your knees in water and your legs look like they are folded forward. The kid is both interested and shows deductive skills, but fails to grasp the truth by quite some margin. What will you answer as a parent or a teacher or as that random guy in the street who can't believe that a kid would come up to him and ask such a question? Perhaps you start talking about fabrics with weights in them. You know, like the gravitational wells at your local science center. For in this way, one has to imagine gravitational lensing. Light follows a straight line which starts at its source and follows the curvature of our fabric around the foreground. No, let's stop. We have already established that this is not an explanation. Let us rather admit that we should probably not be so surprised about physics being so alien to many people. Curiosity isn't lacking, but it is challenging to get a hold of, since physics deals with things that seem to have no deep, satisfactory explanation. And what is worse, the thoughts I've just uttered don't apply only to gravity. They apply to quantum physics, aerodynamics, the Big Bang, whatever that is, and the particle wave duality. With respect to these and many, many other topics like them, it is simply necessary for us to invent something that resembles an explanation. We do so happily, and the more we use the images we think up, the more we tend to accept them as reality. Don't deny it, but try to pay attention to what you say and do in everyday life. We are humans. Humans do things like this all the time. Back to gravity. And for some reason, my daughter. When she was around 1 year old, her favorite game was to drop stuff. Her eyes eagerly followed every Lego giraffe, teddy bear or porridge plate which she pushed over the side of the table. Then she would smile at me. I usually sat on the floor already, prepared as I was. Did she know what gravity is? That is a weird question in many ways. It has a rather obvious answer too. Then consider this. Do you know what gravity is? Of course you do. And that is weird, isn't it? Why do you know what gravity is while my daughter didn't? How can you know it? How can we know what gravity is? We know it because it is part of us. We humans have developed into what we are now over millions of years. Gravity has been with us the whole time. We have raised ourselves upright and become bipedal despite gravity. No, I shouldn't say despite. Without gravity, we wouldn't exist, but that is a different story altogether. Gravity is part of what defines us as humans. Now, even though a grown-up person has some sort of understanding for what gravity is, we will still have to assume that every child grows through his or her own experiences. And to be frank, that process doesn't seem to be too boring either. My daughter, at any rate, laughs heartily when Daddy puts the Lego giraffe back onto the table in front of her. It will be down on the floor again after about 2 seconds. She knows that. There have been many experiments. I know that too. There have been many experiments. And that is just the way of science too, really. One examines and investigates. If the same thing happens often enough, one begins to become more confident about having learned something. So science as a process is not foreign to us. I may even go a step further and state that actually we seem to be born scientists. Children come out of their mothers and begin almost at once to try to find out about things, don't they? Fortunately, some of us manage to stay scientists all our lives. No, this is not meant to be sarcastic at all, for where would we be without those who keep their curiosity throughout their lives, despite life not always rewarding them for their curiosity? What would we do without the Teslas and the Da Vincis of this world? There are innumerable ways for curiosity to manifest itself. The world is filled to the brim with enthusiastic biologists, painters, geologists, architects, and many others. What I want to focus on here, however, is astronomy, since it is the science which, at least traditionally, concerns the universe itself. Astronomy may very well be the oldest of all the disciplines of science. In the beginning, however, the skies and what could be seen there were examined under a premise which is rather different from what we understand to be science today. Don't misunderstand me now. The movements of the sun, the fixed stars, and the quote-unquote wandering stars like Jupiter, Saturn, Mars, and even the rarely appearing Mercury were known already to the Egyptians and other cultures 6,000 years ago. Archaeologists found what is most likely a star map in the tomb of Ramses VI. Yet, and this may not be all that surprising, the movements of the objects in the sky were correlated with stories which guided people in their daily lives. It was all about the blessing of a deity. Perhaps it was also a little bit about power, getting it or keeping it. For example, it was said that the pharaohs had to help the sun god Ra in his underworld fights against the basilisk every night. Without the pharaoh, the sun wouldn't rise the next morning. What a useful thing to take credit for. Then there were the Greeks. The Hellenic culture, which spread over big parts of the Mediterranean for a while, took religion less and less seriously with time. People slowly gained knowledge of what we summarize as geometry today. The measurements of distance was formalized, trigonometry was invented, or should we rather say discovered, so that ideas could be correlated to one another as long as it was possible to express them in terms of geometry. This led to discussions of ideas, which themselves could no longer be heralded by a priest with secret knowledge. A good example for this is Claudius Ptolemaios of Alexandria, Ptolemy for short. His scientific endeavors are amongst the most interesting, in that no one has ever been remembered as selectively as he is. Parts of his work survived about 1400 years in the form of dogma. Ptolemy conducted his first experiments in the year 127 and his last in 151. During that time there was no developed theory of how bodies moved under the influence of forces, which we call mechanics today. Philosophers very often had to come to their own conclusions with respect to the simplest things, or the most difficult things, if one wants to look at it that way. The amazingly accurate answer to life, the universe, and everything was therefore a matter of opinion, and discussed with rather more gusto. The movement of the bodies in the sky turned out to be especially challenging. What does one in fact do without knowledge of mechanics here? One thinks beauty. Simple as that. What is beautiful has to be true. Ptolemy thought this to be the case, and many others did too. It simply had to be possible to explain the movement of the heavenly bodies with the help of perfect geometrical shapes, such as circles and spheres, whatever it was that made a circle or sphere perfect to a Hellenic philosopher. Ptolemy actually managed to do this. He found a way to explain all movement in the sky as he knew it, with the help of circles and spheres. But let us start, as it were, at the beginning. The first observation Ptolemy made was that Earth had to be a sphere. Why? He noticed the same things we know and see today, that is, the horizon and how objects close to it behave, as well as the change in the star map as one moves in north-south direction. Yes, to us pictures of the Earth taken by astronauts and space probes do help a little too, but these pictures are not necessary to draw a conclusion here. It is worth noting too that the spherical Earth is something people did not believe in for 1400 years afterwards. The next problem then became how such a sphere would be fastened in space. What was it fastened to? Ptolemy's answer was rather ingenious. No matter where one went, things always fell down. If Earth was a sphere, that meant that everything fell towards a common center, inwards, if you will. But if that was the case, then why would Earth have to be fastened to anything at all? If a bit of Earth were ripped out, the only thing it would do is fall back. He concluded, on the basis of experiments and observation, that Earth hovered freely in space, with sky on all sides around it. Let the gravity, yes, that pun is intended, of this conclusion in the 2nd century sink in before we continue. Ptolemy observed the stars as well. What he saw led him to believe that they were fixed to the inside of another sphere and that the Earth was the center of this other sphere. But since he had also found out that the stars shone with the same intensity at different places on Earth, he concluded that Earth's dimensions had to be minuscule when compared to those of the heavenly sphere. Now, realizing that Ptolemy came as far as this in his conclusions, the next step seems at first to be rather surprising. He concluded that it had to be the heavenly sphere which rotated, not the Earth. Think about this yourselves for a moment. Which is more likely to be the one rotating, the Earth or the immense heavenly sphere? What does physics, or indeed common sense, say about these distant stars as they rotate once per day around 360 degrees? The stars are very, very fast, that is what it says. Much too fast, in fact. As far as we understand, Ptolemy knew about this rather well, too. It is possible to start asking then why he stood by a non-rotating Earth, even convincing others of his idea. It is said that he could not find a satisfactory answer to the question as to why the air would rotate with the planet. He thought it couldn't. Don't ask why. It's a mystery, of sorts, at least to me. On to the sun, the moon, and the planets. Sun and moon were rather easy to explain. They moved in circles around the Earth. The planets, however, were a different story. They seemed, at times, to move backwards. It is quite an achievement of Ptolemy's that he managed to explain this motion with the help of circles. I mean, he postulated that the planets moved in epicycles, that is, described circular movements on top of a circular movement. Perfect, beautiful epicycles, the way it was supposed to be. What is beautiful had to be true. But does it help to understand? It took around 1400 years before circles had to give way as forms with which to describe planetary motion. But when this first happened, other beautiful ideas had to be dropped too. Speaking of Ptolemy, one of the hidden wonders of history is that rather consciously selected parts of his teachings survived for around 1400 years as doctrines. As we continue now, we will not stay to talk about the contributions of Arabic, Indian, and Chinese astronomers, who sometimes disproved, sometimes confirmed, and further developed the knowledge of the Hellenic philosophers. We will also walk past those few scattered monks and Christian philosophers who tried to adjust the old knowledge to the dogma of the Church. We can't forget all these valuable contributions, of course, but for the purposes of this particular story, it is most effective to discuss at once one Nicolaus Copernicus. Copernicus was not the first to conclude that the Earth could not be the center of the universe. Amongst others, Pythagoras, he of the triangles, most likely came to this conclusion too, albeit in a somewhat, interesting manner. Check it for yourself, it's worth it. Copernicus couldn't see how Ptolemy's argument against the rotation of Earth was true. There were additional questions. If there was a heavenly sphere, what was it made of? What would the outside of that sphere have looked like? Perhaps the outside of the sphere was the abode of God. What pious Copernicus thought when his mind took him to pondering the heavens isn't known. It is undisputed, however, that to him there had to be a different solution. The Earth could hardly be the center of everything. The problem then became how the Earth could be stationary if it wasn't the center everything fell towards. Or was it stationary at all? To Copernicus it came rather naturally to assume that the Earth could move, and if the Earth did that, the question of how everything moved in relation to each other had to be answered anew. But how? Start with the idea of relativity. Something that doesn't move looks as if it moves backwards to somebody who does move. Copernicus read and pondered and examined observational results and arrived in the end at his version of what we now call the heliocentric model. And you know what that was? A collection of perfect circles. That's what it was. Copernicus was, after all, a pious man. Next up was Tycho de Brahe, a 17-year-old from Denmark, who noticed that the position of the wandering stars did not quite agree with the day's theories about where they should be. He started long-term observations of planetary movement. The result of this work was data accumulated over 20 years, all that without a telescope too. These were, in fact, 20 years of data which young Johannes Kepler received at Tycho's deathbed. What Kepler saw in Tycho's data was that the planets did not move in circles and not at all in epicycles. The only way to explain Tycho's data was to assume that the planets moved in elliptic orbits with the Sun in one of the focal points of the ellipse. But wait, we know today that the planets move in orbits which are almost circles. So was it really possible for Tycho to observe that accurately without the help of telescopes, to recognize these tiny elongations in the planet's orbits? Well, yes, at least in the case of Mars, which has a slightly more elongated orbit than the other planets. And thankfully, Mars had become one of the focal points, as it were, of observation for Tycho. A snap of the fingers later, and gone were the circles. After Kepler, or maybe with Kepler, mathematics was introduced into the equation. Research was still all about the movements of the planets, but the calculations became more and more complex with time. In fact, they became so complex that the next scientist in our series had to invent his own way of computing things. Of course, we talk about calculus and the man with or without the needle in his eye socket, Sir Isaac Newton. By the way, Newton was not the only one during this time who developed calculus. Gottfried Leibniz did the same in Germany. Today we use Leibniz's notation, while Newton used the newly found mathematics to a much greater degree than the German mathematician. Anyway, Newton thought that if an object is picked up from the ground and then let go, it will increase its speed on the way down. If one lets it go from a greater height, it will be faster when it hits the ground. And that is not a surprise at all. My daughter has in fact come as far as that too. But Newton noticed two things here. Firstly, it was rather natural to assume that whatever drew the object to the ground became weaker at greater height. Secondly, it seemed as if there was no obvious boundary height at which that force would stop to exist. It would have to become weaker with distance, but would never completely disappear. This meant, amongst other things, that the moon had to feel it too. Yet the moon doesn't fall down. With the help of the mathematical tools he himself was so instrumental in developing, Newton found out that it would fall down if it ever stopped moving laterally. The object which is at rest before it is let go will fall down, while the moon is not at rest and does not. In other words, the vertical force at work on the object or the moon not only could be but had to be the same. We call this force gravity. After this, the rest became rather apparent. If the moon was held in place in orbit around Earth by gravity, then gravity had to be responsible for the orbits of the planets around the Sun too. Newton could derive Kepler's laws mathematically and ended up doing nothing less than presenting to the world the first scientific and all-inclusive theory for life, the universe, and everything. The universe, anyway. And this was a universe which could be described by mathematical formulas. A universe which could be described by physics. This is Newton's mechanics. Do you know the feeling? That is the feeling of working on something so hard as to exhaust yourself and finally having it all come together in some few symbols and letters, expressing physical quantities. F equals m times a. There is satisfaction in that. It is a sort of mathematical catharsis. It is like the first cup of coffee in the new house which one has built with one's own two hands. It is, in one word, beautiful. How Newton would have reacted to being confronted with thoughts like this is anybody's guess. All indications point towards these kind of considerations being somewhat foreign to him. The truth is that very few scientists during Newton's time even had the chance to experience something similar to mathematical catharsis. Just take Galileo Galilei. Galileo had to defend his life and his science in a much more direct manner than many of the others for saying that the heavens weren't perfect. He used his telescope to show that the sun had spots, that there were craters on the moon and many other things like this. He simply showed that the objects in the sky weren't perfect or beautiful, as the church claimed they should be. But then tell me that the sun, with its intertwining flows of radiating plasma and its spots which may or may not explode into the solar system, isn't beautiful. You can't say that without lying, right? Perhaps, only perhaps, what is beautiful doesn't have to be true, but what is true is beautiful. Isaac Newton formulated a theory for all of the universe known at the time, yet that was only part of his scientific work. Before he even spent one thought on mechanics, Newton laid the foundation of what is the most important observational tool of exploring the much greater known universe of today. There is no hyperbole in that paragraph. Young Newton was rather observant of his surroundings. To take an example, he wondered about where the colors of the rainbow would come from. In order to find out, he constructed experiments, one of which showed what happened. When a ray of light from the sun is isolated through a hole in the wall, then this ray can be led into a prism where the colors are separated, and the ray as a whole is taken off its original path as well. The men of the church didn't protest. They probably should have, since this experiment showed that even the heavenly light itself was not perfect. But then, of course, a rainbow is undoubtedly beautiful, and the knowledge of how it comes about does not need to subtract anything from the experience. In fact, one may argue that knowledge only adds to the fascination. At any rate, being able to split light into its colors made it possible to examine the nature of its source, and the nature of what lay in between the source and the observer. The concept one needs to understand this is that of the wavelength and some quantum physics. The shorter the wavelength, the more energy the light has. Violet light, for example, has more energy than red light, since its wavelength is smaller. By the way, did you know that we cannot actually see all the colors of the spectrum the sun sends out, but only those at wavelengths from roughly 400 to 700 nanometers? When thinking of the sun's spectrum of colors, which is vast compared to what our eyes pick up, one could imagine that a plot of it would have to be a nice and smooth line, running from lower to higher wavelengths. Perhaps you know enough physics to know the shape of that line too, the so-called black body spectrum. The actual spectrum of sunlight isn't like that though. Well, it's close, but not quite. It looks rather more like something is missing at some places. These bite-outs we call absorption lines, which in this case are due to the Earth's atmosphere between us and the Sun. How? An atom or molecule has different energy levels, which restricts the atom to only absorb or send out light of a particular wavelength. The molecules and atoms in the air all have such energy levels and absorb light of different wavelengths to different degrees. Turning the argument around, this means that light of a particular wavelength can be correlated to a particular chemical element. The light's intensity then gives us information on how much of this element is present in the light source, and by building instruments which can see wavelengths our eyes cannot, the opportunities and possibilities for observation became enormous. One can, for example, find out that there is a lot of hydrogen in the universe and why that is the case. One can find out about the structure of the universe around us and about how the Sun belongs to a galaxy of around 400 billion stars, such that on the whole, it is not really all that special in the cosmic perspective. Another thing entirely is that everything in the universe seems to be moving away from us. Truth be told, it may seem to the observer that the universe itself is expanding. This means that everything was very close to each other once. We think that at one point there was nothing, which exploded. That is a Pratchett quote, and also a rather big conclusion, and perhaps it's not self-evident anymore where this conclusion is drawn from. What we have to talk about here are mathematical models, that is, solutions to sets of equations, in particular to the Einstein field equations. The variables in these equations can be the time or the average distance of objects in the universe to each other, or a host of other things, and the solutions to the equations give us information about how these variables develop with respect to each other. There is a problem, however. Einstein's system of equations is so complex that the solutions give information only under a certain set of conditions. At the time the universe began, for example, our solutions are infinite. They don't work. To repeat, we have models, equations that is, which describe the beginning and progression of the universe to whatever fate it may have. Yet we have no way of interpreting these equations as a whole. Still, we think that in the beginning there was nothing, which exploded. We expressed this rather directly. We have even given it a by now famous name, the Big Bang. The Big Bang theory is not the only example of this either. In the same system of equations by Einstein, one can also find black holes. These have inspired human imagination about as far as anything, with their own Hollywood movies, countless novels and comic book stories, as well as the odd kid choosing astrophysics as a profession in order to find out about them. Big Bang and black holes are inventions, virtually empty expressions, which are used to conjure a kind of description of the physical phenomena in question. There is nothing explosive about the Big Bang. That doesn't mean that the researchers are wrong, or worse, that they can be charged with a scientist's equivalent to heterodoxy. The scientists who communicate this knowledge know what they are talking about, so when the cameras are turned off, the words change. There are less explosions out of nothing, and more approximation limits, models and singularities. There are many mathematical approximation techniques, some of which bear strange names like perturbation theory, which make it possible to examine what happens when our models break down. The only things that are needed are a little experience in mathematics, the knowledge that we deal in approximations and not truths, and enough time to work intensively with the equations over an extended period of time. When we have gained enough experience, we begin to understand. This is just as true for my daughter learning about gravitation as it is for, say, the medieval church builder or, Brian Cox finding a good way to present the physics behind black holes on TV. There is no principal difference for any of these three examples. Learning about physics itself is like this too. It is about finding mathematical equations and then using them often enough, while ever changing the conditions applied to them. It is about learning what the equations can, and perhaps more importantly what they cannot describe. Then understanding will, at the end, arise more or less by itself. Remember how this tale began, and how it developed. The way the world's thinkers approached the biggest problems never stopped changing. First, there was the mythical approach, which got softened and slightly changed by the advent of geometry and its reliance on the truth behind beauty, all the way to mathematical equations, from what can be grasped to the ungraspable. It had to be like this, didn't it? For the questions have not and never will end while human imagination does have its limits. Let us focus again on black holes towards the end. The whole point with those is that they draw to them all information around them. How would you know anything about them then? They should be invisible, simply invisible, unimaginable, if that is a word. Yet people have predicted, discovered, and imaged them. Think about it all for a second. Mathematics is nothing less than the mightiest tool at our disposal when our imagination has reached its limits. On the boredom induced by magnetic fields. Let's talk about that for a second, shall we? Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. Yes, I'm supposed to be kind. I'm not perfect. When talking about magnetic fields being boring, well, let's put it this way. English country gentlemen are known for their outbursts of self-righteous indignation. I'll try to be gentle in the same way, but I'll probably fail. 'Cause, everybody remembers them from school, surely. Those little pieces of iron on a surface that align in weird shapes when you put a magnet on them. We all remember that as boring. Why do I have to learn about this? Boring. I mean, there's no interest in magnetic fields, right? Apart from the demagnetization of credit cards. Maybe. And why would there be? In everyday life, that and fridge magnets. What more is there to care about? Even if we try to drum up a little sympathy for physics, and we most certainly can, we may fail. Take, for example, the Earth's magnetic field. Forget the fridge, this is the whole friggin' planet. Well, the Earth's magnetic field is rather weak, to be honest. It's strong enough, however, to deflect most of the solar wind particles thrown at us by the sun. Whatever enters the Earth's atmosphere creates a wonderful show on the night sky, aurora borealis. Without the deflection of the solar wind, Earth would look like Mars. We'd all be dead. You didn't see that one coming, right? No, but those magnetic fields are still rather abstract, passive constructs, you may say. The active part in all of this is played by the particles, by electrons and protons. If they'd hit us, we'd be dead. So even though the Earth's magnetic field is in fact life-savingly important to us, it doesn't really feel interesting. What about the sun? On it, the biggest explosions in the solar system take place, so-called solar storms, which are connected to X-ray events called solar flares. Solar storms happen when the sun's magnetic field turns in on itself and becomes compressed to the point of snapping. Yes, but here the driving force is differential rotation, you say. It is the fact that the solar gas or plasma rotates faster at the equator than it does at the poles, which leads to all sorts of shenanigans. So it is the weird rotation of the sun that is interesting, not the dull magnetic field. Alright, I hear you. I must admit that you are a rather difficult case, as I believe both aurora, solar flares, as well as your and my sheer existence to be impressive, but still, I think you are looking for a more active, creative, or for that matter, destructive magnetic field. And I have something for you, if you don't mind. Neutron stars. Neutron stars are the densest things this side of a black hole event horizon. Their size is comparable to that of a small city, around 10 to 20 kilometers in diameter, while having a larger mass than the Sun. They consist almost entirely of neutrons and are protected from further collapse by quantum physical effects, balancing out the immense force of gravity. This is where things get interesting. First now, I wrote they consist almost entirely of neutrons. That is wrong. 20% of the neutron star consists of electrically charged protons and electrons. So the moment our star rotates, there will be a magnetic field. Actually, it's not quite as simple as that either. The magnetic fields of neutron stars are composed of frozen-in remnants of supernova magnetic fields and dynamo-driven rotational magnetic fields of the kind that I have just described. In fact, a neutron star's magnetic field can be several trillion times stronger than the Earth's, or the Sun's magnetic field for that matter. Under normal circumstances, that magnetic field is rather predictable. In pulsars, it radiates energy from the star in the form of X-rays, and does so constantly for a significant amount of time. When the magnetic field of a neutron star reaches several quadrillion times the strength of the Earth's or the Sun's magnetic field, we call the object in question a magnetar. Strangely enough, magnetars rotate more slowly than ordinary neutron stars. Their magnetic fields are dominated by the supernova leftover component and stay the way they are due to superconduction inside the star, probably. It's all a bit fuzzy and not well understood. Quite frankly, magnetars and their magnetic fields are the most boring thing you will encounter in the whole universe, and I'm not facetious at all now. Your attitude has definitely not made me facetious at this point. Let me give you an example in order to summarize. SGR 1806-20, as it is called, is the closest magnetar we know of. It lies in the constellation of Sagittarius on the other side of the Milky Way, around 50,000 light-years from the solar system. Its diameter is around 20 kilometers. Its rotation speed is once every 7.5 seconds. The magnetar's surface, which is only 10 kilometers from the center, turns at a whopping 30,000 kilometers an hour, which, all things considered, is a slow rotational speed. Together with the frozen-in component, the magnetic field of SGR 1806-20 then becomes 1,000,000,000,000,000 Tesla. Eat your heart out. What such a magnetic field could do, besides demagnetizing credit cards? I'm sure glad you asked. As it seems, I have finally gotten your attention. This is what such a magnetic field could do. If the Earth were to come to around 1,000 kilometers distance to this or any other magnetar, the strength of its magnetic field would render your bioelectromagnetics, as it's called, non-existent. The atoms in your body would break down, and you as a person would dissolve into a slush of subatomic particles, a demagnetized human, if you will. That is about the most boring thing ever, right? Listen, we've already forgotten about fridge magnets. Let's forget about credit cards too. Nature is not boring. She is awesome the way she is, and a lot of her is conducted by electromagnetic fields. You may blame your teacher for not really telling you all about it when you were in school, or you may look in the mirror and tell yourself that you are just, well, anything from not really interested to plain lazy. Nobody is holding you back from realizing this. From touching stuff to TV, macroscopic nature is all about electromagnetic fields. When I see the northern lights, I see life. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thanks. The northern lights, that green velvety curtain dances over the sky, inspiring countless stories of everything from dark warlike gods awakening to ancestors playing football with enemy skulls after the war, and poetry of wars too, I'm sure. This story is not that story, even though I appreciate the legends, which aren't just about war, by the way. I still can't quite wrap my head around the idea of the lights dancing. Now, I'm not dismissing the idea. Both the legends and the imagination that comes with them are too beautiful to not warrant their own piece at one point. No, it's not that. To me, there's just something much bigger to uncover than legends and dancing. And all you need to do to get there too is to stay with me for a while. Hop over whatever physics distresses you, but also take away whatever physics you do find comfortable to think about. Challenge yourself. Follow me. Den tingen som du ofte har spurt om, hva det kan være som grønlendingene kaller nordlys, det er jeg ikke så særs kynnig i, og jeg har ofte råka folk som har vært på Grønland i lang tid, og de synes ikke ha fullvis kunnskap om hva det er. Ellers er det slik med den tingen som med de fleste andre som folk ikke kjenner med visse, at vittuge menn gir seg ei mening og gissing om deg, og tror slikt om det som syntes deg vanligast og rimeligast. Den naturen og hotten er det med nordlyset at det er alltid så mye lysere som natta i seg sjøl er mørkere, og det synes jeg alltid om natta. Men aldri om dagen og oftast i koldmøre, men sjelden i måneskinn, og det er såleis å sjå som ein ser ein snor laga ein svær eld langt unna. Det ser ut liksom det fra denne skytkvasse oddar opp i lufta, ulykke på høgd og mykje urolige, så at snart kjem den ene høgst og snart den andre, og alt dette lyset skifter såleis at det er som en blakrande kige å sjå til. Men medan disse strålene er på det høgste og bjartaste, da står det så mykje lys av deg at folk som er ute kan godt fare sine veier, og like ens gå på veiding om det trengde. Og om folk sitter inne i husa sine og så sjåen ligger over jorden, da er det så lyst inne at alle som er i huset kjenner hverandre. Did you understand anything? If yes, you're probably a little miffed at my pronunciation of this, say, rather vintage edition of Norwegian. Yes or no, it's all good though. The point is that there were texts such as this, the King's Mirror, which discussed the Northern Lights in more or less academic terms in the 13th century. And what I just read for you was part of an educational dialogue between father and son, starting with, "You know the thing you always go on about? Yeah, neither me nor all the wise men really know what it is, but make no mistake, we're studying it, and we've got some ideas too." That's it, basically. In other words, they were asking questions about the Northern Lights, and they were looking for answers too. One of those questions was, where do the colors come from? As in, forget the stories, what really happens here? Today we know the answer lies in quantum effects involving atmospheric particles colliding with electrons and ions. It's about energy exchange. It always is. I mean, collisions are never easy to handle properly, but they can always be understood in terms of energy exchange. Imagine a car crashing into a wall. The energy of the car's movement will, at the end, be used to deform the car, and perhaps the wall a little too. In quantum collisions, the energy of the incoming particle will, at the end, be used to create a photon. Light, that is. There are a couple of steps in the middle there. The atmospheric particle absorbs the energy first, then gets rid of it in the form of light. And that's a good thing for us, because the color of the light sent out is characteristic for the respective atmospheric particle. Like, we will know what sent out the light. Oxygen atoms, for instance, can only radiate particular types of green and red. Well, no, quantum theory gives other opportunities too, but those are the colors we can't see, or they are not intense enough for our eyes to detect. Still, we know that northern lights in photographs usually show oxygen atoms. Now, granted, we're not talking about large amounts of energy per collision, but then once in a while, 1 billion of these collisions occur at the same time at the same place because there are just that many particles in the atmosphere and a comparable amount of other ones streaming in. Thus, the sky lights up. Wait a second, streaming in? So we're talking about particles from the outside, streaming into the Earth's atmosphere. And if they are on the outside of Earth's atmosphere, they are on the outside of Earth's magnetic field. That's relevant because most of the electrons and ions we're thinking of just wash by Earth, thankfully. They can't get into the atmosphere because of their interaction with our magnetic field. Yet, sometimes, some particles enter the Earth's magnetosphere, as it is called, which wraps around the atmosphere like a just slightly imperfect electromagnetic shield. The physical process behind that imperfection is called magnetic recombination. It's wonderfully absurd physics. I mean, one way to describe it would be to say that magnetic fields melt together under the right circumstances. Not too often, though. Only sometimes. It's got to do with what is called Alfvén's theorem and frozen-in magnetic fields. Well, think about it this way. One can assign so-called field lines to magnetic fields. The idea is to draw a line where a charged particle would move, kind of. The particles usually follow a sort of helix track. The center of that helix movement would be where we draw our magnetic field line. Got that? It's school physics, but probably a part of school physics you, like me, wanted to forget as soon as it was possible to do so. Still, magnetic recombination is a process during which these imaginary field lines realign. Only that means that the particles move differently in all senses. They'll have a different direction, and they'll also be much faster than before. So as weird as this is, the process of imaginary field lines realigning has quite real consequences. It comes down to energy exchange. Yes, this too. See, it turns out that magnetic fields have what is called potential energy. You probably know the term from school again, but if you don't, the idea with potential energy is that if you ain't doing something about it, stuff will happen. You ain't holding up that apple, it'll fall. That kind of thing. The electrons and ions push against the Earth's magnetic field, which holds on until it can't anymore. The can't anymore, quote-unquote, happens under very specific circumstances. But when it does happen, the proverbial apple will fall, and in this case, charged particles will not just enter the Earth's atmosphere, but will accelerate along the field lines of the Earth's magnetic field and be there to collide billions of times at the same time and at the same place with atmospheric particles. All right. Where do those charged particles come from then? Honestly, where do those charged particles come from? And what did I mean by most of them washing by Earth, thankfully, quote unquote? The truth of the matter is that the sun constantly sends out electrons and ions. The solar wind is a steady stream of electrons and ions emanating from her, from the corona to be precise. It fills the whole solar system. It's enormous and can obliterate the environment on a planet. Look at Mars. It used to have a magnetic field. It used to have an atmosphere too, and we think liquid water and all that. But it doesn't anymore. Why? Because it lost its magnetic field, and without it the solar wind was free to quite literally blow the environment on Mars away. This also means that the sun loses particles, constantly. Yet that doesn't really matter. There's just too much matter in her for this to make a difference. She's 1.4 million kilometers in diameter, after all. Now, there is a little detail to everything I just said a minute ago. We wouldn't see the northern lights if that was the whole story. No, in order to produce aurora, the solar wind needs to be enhanced, made stronger so that it can push against Earth's magnetic field enough for magnetic recombination to happen. But no worries, the sun's surface explodes once in a while, you know? That very same process, magnetic recombination, happens on the sun too, when her magnetic field turns in on itself and creates these wonderful loops you can sometimes see on TV or online. When the loop becomes too tight at the bottom, the whole thing can explode. At the base of these explosions are what is called sunspots. You've heard about them, surely. Wait now, why would the sun's magnetic field turn in on itself like that to begin with? Because it is created by particle streams under the surface which are quite literally convection streams, like the thermics eagles use to soar up high into the atmosphere. particles stream upwards until they cool enough to sink down again. Of course, particles here are electrically charged too, and that produces a magnetic field. The problem is that the sun doesn't rotate at the same speed everywhere, so those convection streams get distorted after a while and can ultimately lead to exploding loops of plasma, so-called solar storms. Okay, now, the question is quite apparent. Why doesn't the sun rotate with a constant speed everywhere, like Earth does, for example? See, when the sun was born, she drew in matter from a disk of rotating stuff. That disk blobbed in the middle, kind of, is what I'm saying. And on top and bottom of that bulge, the rotation slowed down a tad. The blob became the sun, and her rotation follows the same pattern still. Faster rotation in the center, slower rotation at the poles. The difference is around 10 days per rotation, or thereabouts. And the particle streams which create the sun's magnetic field get twisted by that weird difference in rotational speed. In addition, in thermics, the rising air cools down and sinks again at one point precisely because it gets colder higher up. With lower temperatures comes lower pressure too, and that's because of lower density. Turns out in the sun everything is determined by density. The further down you go into the sun, the denser she gets. In fact, in the center she is so tightly packed that the ions there, it's a plasma, ionized gas really, fuse together to become other ions. Hydrogen becomes helium, if you're wondering. When I was teaching, there was always that one student, the one who would be rather annoyed at this point and say something along the lines of, "Okay, what's next? Are we going to talk about where hydrogen comes from too? I thought this was about the northern lights." You know how hydrogen was made, right? Turns out we can take this all the way to the beginning of the universe. Do we want to? I kinda do, but then we can also just turn around and think about northern lights in a more usual sense. I mean, on TV or online, this story is usually, quote-unquote, told the other way round. And no, we don't start at the beginning of the universe. We start deep inside the sun, in her core, where hydrogen fuses into helium, releasing energy that to start with has nowhere to go. So it pushes outwards in the form of radiation until it gets just a little more space and starts accelerating particles which then form convective currents, pushing upwards and outwards. This can take several hundreds of thousands of years, by the way, until energy breaks free into the solar system in the form of light and, of course, the solar wind. Truth be told, the solar wind is always there, but sometimes when explosions happen on the sun, it has a little extra oomph in it. And when that happens, there might just be a visible aurora on Earth a couple of days later because the extra pressure might make Earth's magnetic field give way just a little. So, some of the solar wind may enter the Earth's atmosphere. Its particles colliding with the atmosphere's atoms, ions and molecules. And if this happens often enough, a couple of billion times at the same place and the same time, we can see the light created by these collisions, the aurora, standing there in the middle of nowhere, looking up and pondering. And thus it is. Whenever I look up, I see the colors in the Earth's atmosphere. I see Earth's magnetic field lines being made visible by those lights. And I ponder. I ponder the energy from the sun. Atmosphere, magnetic field, solar energy. Those are the ingredients of aurora. Without them, there is no aurora. But this is, in a very real sense also, the triumvirate of life on Earth. Take away one of them, and we'd all be dead, or more likely, would have never come into existence. When I see the northern lights, I see life. Why do stars have different sizes? Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. It's a good question, right? There are giants and dwarves and even smaller neutron stars. Why are they as big as they are? Take the sun, for example. When reading about how the sun came about, things get complicated in a hurry. We talk about matter in a cloud which becomes so dense that nuclear fusion is possible. Somewhere. There's only one place where that happens. Well, there can be more than one, but we'll keep it simple, okay? Let's assume one place in the cloud where matter accumulates big time. The start of fusion reactions is the point of birth for a star. It's gas dynamics and, nuclear fusion we talk about, so yes, it's complicated in all sorts of ways. I'll show you how to extract information from this mess without having to be a genius. Let's talk gravitation. No, not Einstein's space-time and all that. That'd be complex again. No, we stay with our own daily experience, with the force that points downwards. TFTPD, if you will. No, it's not called that. Its name is weight. We think about weight, not more than that. Don't ask what gravitation actually is or something. Stuff falls down and weight is what makes it do that. Stuff includes you. You fall down too. So weight, right. As it happens, nuclear fusion starts where there is most matter. Weight makes you fall towards where there is most matter. Downwards becomes meaningful. It denotes the direction of where our star is born. Matter just keeps accumulating there. That's good. However, this accumulation does not continue into eternity. The Sun, for example, is 1.4 million kilometers wide after all. It has been for quite a while already. So there's something else there too. Radiation pressure, quote unquote. And yes, I will forgive you for thinking, here we go again, this isn't going to be easy. And it isn't. Make yourself a cup of cocoa and go read for yourselves if you're interested in what radiation pressure is. You'll need that cocoa too. Right here, we'll swiftly move on. What's important is the relation between radiation pressure and, well, we're not thinking about any particular object falling anywhere, just plasma reacting with plasma in weird ways. So it's not really weight after all, it's TFTPD. Sorry, but you get the idea, right? One force pushes outwards, the other pushes inwards. They give us the sun's size, the equilibrium between the two, you may say. If the radiation pressure decreases, for example, then the sun will decrease in size with it. Radiation pressure isn't always what pushes back. I'll put a link into the description leading you to a piece about magnetic fields and magnetars. These are neutron stars. In neutron stars, some weird quantum stuff pushes back, but there's always something pushing back against gravitation. Equilibrium of two forces, that's it. Energy makes things happen. Hi, my name's Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. Energy makes things happen. This is perhaps the simplest explanation of the term. And you know what? I have no problem using that explanation either, even though one might argue that it is a definition of what we put into the expression, not an actual definition of the term itself. We always use that sentence within a given framework, let's say as a teacher in the classroom. we fill the term energy with meaning and give it context in this way. Eventually, it takes patience to learn physics. And when you know energy, you pretty much know physics. Let's assume for a second that we already know what energy is. For physics is fundamentally about the following three questions. 1. Where is the energy now? 2. From whence, as they say, did the energy come? And 3. What happened along the way? Here's an example. We see Jupiter in the night sky. Jupiter is a planet. It's further away than you think. I mean, it is. How do we answer those questions? 1. The energy sits in the light which hits our eyes. 2. The energy comes from the sun which has radiated it. 3. The light hit Jupiter only to be scattered in all directions. Sorry, that's it really. Another more down-to-earth example is baseball, specifically pitching. The physics of baseball pitches is quite a bit more complex than one should think. Questions 1 and 3 are okay. The energy is in the movement of the ball, while the ball got its speed from being thrown. But where was the energy to begin with? The pitcher stands still before he starts moving like only baseball pitchers do. Does the energy wait in the body until it can finally be convulsed out into the ball like that? That's strange. Perhaps we just misunderstood something. So what is energy? In truth, I have no answer. Gee, thanks, you may say. For if we go back to the classroom, we can say we are teachers. Then we have students, and we are supposed to explain what energy is. The curriculum says so. The curriculum says that the students shall know what energy is, and we as teachers shall test the students on whether they do. Period. I mean, we can't do it like Newton and just think up our own reality. Or can we? Well, Newton hasn't really dreamt up his own reality either, to be honest. But we can still follow Newton's thoughts and see what happened. There's no apple at play, but Newton saw that an object falling from greater height hits the ground at higher speed. The speed increases during the fall. You've seen that too. It's intuitive. Energy as a concept is not important here, I think. We can show our students the equations and get them to work without talking about energy. You all know these equations. Even the pacifists among you have probably used them to calculate the landing place of bombs and other projectiles while being in school. When I was in school, I hated them. When I was at university, I started loving them. You derive from speed to velocity to acceleration and integrate the other way round. Most of all, you can see and measure that they describe your experiments properly. That is a beautiful insight in itself. Then we can introduce energy as an abstract concept and give a good reason for a missing definition. Because nothing in science is simple. You can be excused for not being able to put one and one together at all times. In fact, researchers do excuse each other for this. Just take the example of the projectiles again. Mostly, we calculate the trajectory without taking the resistance of air into account. Think about it. Once we do, things become very, and I mean very difficult. The first thing we do whenever something is completely new to us is always to find what isn't changing during a physical process. When using lasers for speed measurements, for example, we use the fact that the speed of light does not change significantly while traveling through air. So it's important to know what stays constant. But we can't expect nature to always follow our thoughts. And that means that what stays constant doesn't need to be something we can easily grasp. Energy is simply one of those things. We use it because the total energy of a system never changes, whatever happens to that system. And when first starting to use the concept, we will recognize it in all sorts of contexts. Take the falling apples. It's the standard school example. Potential energy is being transformed into kinetic energy. Height becomes speed. Turn that motion sideways and you get a car hitting something harder than itself. The energy was at first kinetic, that is, in the speed of the car. Where is it now? Well, it's been used for something, deforming the car. That doesn't happen by itself. Speaking about collisions, on the atomic scale, collision and a host of other ways to transfer energy lead to, wait for it, chemistry. Granted, not all the bubbly stuff happening in beakers are collision-related reactions, but every reaction has to do with energy. which is transferred from one substance to another. In fact, chemists are increasingly becoming interested in looking at reactions in terms of energy. Once you do that properly, you enter physics, quantum physics to be exact. I know a few chemists who hate the idea of doing physics and even more who love it, but one thing is for certain: the subjects of chemistry and physics start melting into each other by means of energy. But enough about the abstract stuff, let's talk big balls. Sorry. I just mean that we can calculate what planets do and how they move by means of energy. We can do the same thing with the flight of smaller balls, like baseballs. I'm talking baseballs. It is all about energy, which is a concept we really can't describe better than through maths. We learn about it through experience in doing the maths. Energy is just something that doesn't change much, that's all. Well, I've talked about the story of the Northern Lights a couple of times. Other people have done so too. It's a story that is quite easily told, but there's something about it that I think one shouldn't forget. Think about it. Think about, energy being released in the center of the sun by means of, fusion reactions. Hydrogen becomes helium, and then the energy takes a couple of 100,000 years to travel to the surface of the sun, and then, there it is released into interstellar space by means of radiation or particles. And that's fine, because especially the particles are interesting with respect to the Northern Lights then. And sometimes, those particles, the so-called solar wind, enters Earth's atmosphere, where the particles themselves collide with oxygen and nitrogen and the elements in the Earth's atmosphere, and from that collision derives the light that we see dancing on the sky or in the sky. But one of the things that, to me at least, is most interesting about all of this is that the moment you go deeper into it than this particular story, well, you need to study physics at university to really understand. You can say, come on, that's not true. I understand what Northern Lights are, but then I can also challenge you already with the concept of a particle. What is a particle? If you've taken physics at school till the end, you may have heard of the particle wave duality. And if you're like me, you go through these lessons and you're utterly confused by the way these expressions are used. What is a particle? A particle can behave like a wave, but then you kind of separate it also from the expression wave when you talk about the particle wave duality, and it all becomes just fuzzy and weird. And if you had a good teacher, then he's shown you the experiments, but he's also told you that if you start doing the maths, and you do so properly, which means you first of all understand what a mathematical model is and how you use it. There's a video on that on the channel here as well, or then you will end up saying, okay, I got to do the maths in order to understand this, and that's fine, because we know maths, we know how it works, we know how to apply it to nature. And that's the very reason why we find out about all these things, right? So it's quite okay, actually. But in order to understand it when you're not a physicist, when you haven't gone through this process of learning how to apply models to natural situations, well, you're stuck with that story that I just told in half a minute or whatever it was, right? There's nothing more for you to understand apart from that story, unless you go ahead and you study. And you can say, okay, well, now you're getting a little pompous here, and particle is a particle, and why would I want to know more about it? But it's also
a thing of, magnetic fields. Like if you go and watch the video that I've made not too long ago about Northern Lights, then there's a lot of talk about magnetic fields and about a process called magnetic recombination. And what I tell you in that video is that you shouldn't try to imagine what's happening there. It's just something that happens, and we can calculate it. It's Maxwell's equations in this case, which are, well, I shouldn't actually say that, but it's not quantum physics we use here, but it's still maths we use in order to predict or to understand what's happening. It's the same sort of concept. You have models, mathematical models in place, which is ways to describe something, that you've seen in an experiment or in nature, and then you try to make predictions. You experiment some more. You see that your predictions hold, and you start or you continue using these particular mathematical models, the equations basically, for these particular situations. The same thing though, if you cannot understand Northern Lights fully without understanding what magnetic recombination is. But in order to do so, you have to go into the models, you have to go into the equations, you have to work with them until understanding dawns. And if that is something that rings, a bell with you, that I'm very happy about that, because that also means that you've taken as much of a deep dive into this channel as it's probably possible, because that's one of the main points of what I try to say here. It's like it's a matter of spending time with trying to figure out how all of this works. It's not necessarily a thing of a matter of intelligence or whatever. But I digress. But you've got magnetic recombination. You've got the very concept of a particle. And, it just not being the same as the thing you hoover up when you clean your flat or your house. You have all these things surrounding the story that I told you in the beginning of this video here. And that's the thing about Northern Lights. You either take 30 seconds or a minute or so to explain what it is and you're happy with that, or you have to study. And what surprised me as a physicist and a long-time physics student, because I've never stopped studying physics, even though I've got my degrees now and everything, is that people are surprised that you need to learn and to work to understand it all. What other walk of life is there where you don't have to work to understand, to grasp how it all works? They're beautiful, aren't they? These are called light pillars. They're quite a rare optical phenomenon, and this time around they've been observed over a Norwegian town called Steinkjer. I'm probably going to link to a newspaper article, which, to be honest, is behind a paywall, but at the same time, I just wanted you to know where I got the image from, where I got the idea for talking about them from. I haven't read the article though myself. Again, it's behind a paywall. But yeah, these are quite awesome natural phenomena. They're, as I said, they're quite rare as well, and they occur when there's ice crystals building up at one place higher up in the lower atmosphere. But they're building up. They're usually hexagonal in shape. They orientate themselves, or they align with each other in at the same angle. So they're flat crystals, and then as they grow, they just keep sinking, and they reflect sunlight that at this point comes from below. So the sun is below the horizon, sending its light up into the atmosphere. It's dark where you are, and the sky behind the pillars is also dark. So sunlight comes up into the Earth's atmosphere and then gets reflected by these, well, you may call them little mirrors if you want to, but by these hexagonal ice crystals that align pretty much in the same way as they fall. But of course, they're not 100% aligned in the same way. They do move around as they fall. and that means that the light you're actually seeing when you watch these pillars is glittering, beautiful. But it's also, it's also intriguing in the way that if you're like me, right, you're a person who will always ask once more why and how. Like for example, now, it's like there's a process there, right? These crystals build up higher up, as they grow, they fall and so forth. All of that makes sense, but you can take it from there to wherever you want it. You can talk about, the glittering, for example. Why would it make a difference that these little ice crystals do move around and do change the angle a little bit? For me, one of the questions I always come back to is, how do these crystals come about to start with? So-called nucleation. Because to me, it's always been intriguing that at one point you have air, there's water vapor in it, and the next moment there's cloud droplets, there's ice crystals, and then when you ask the question of how that comes about, it's like, well, there's smog in the air or other sort of foreign particles, if you will, and then on top of these, the ice crystallizes out, or the water agglomerates on it, if that's the right word, if that even is a word. But that is not enough for me. Like why would it do that? And then you enter a part of physics and a part of science that is, I shouldn't say a part of science. Science is really just a method, but you enter a part of physics that is quite intriguing in its difficulty, at least to me. These cloud droplets, as they build up, or the crystals in these pillars, right? As they build up, they are, to start with, microscopic objects. You should use quantum mechanics on them, but then they start growing, and at one point they become macroscopic objects. That means you can take flow dynamics and these sort of equations, and you can talk about forces on objects and so forth. And you can calculate stuff with these sort of ideas. But there's a transition region there that is very, very difficult. And of course, we do have models for these as well, but the models are a far cry from being as good for their purpose as quantum mechanics is for microscopic objects, or the whole idea of forces on objects and flow dynamics is for macroscopic objects. So it's right there in the transition region at one point, and it's really not that well understood. And it's the same with these light pillars here. I just stand in front of them, and I admire their beauty, because they are beautiful. But there's always something more to it, and to me that's intriguing. I don't know about you, but there are questions to me that I don't need answers to, because I do remember last time I saw them over the top. Yeah, well, I just remember standing there and going, if I ever knew how this really worked, it would become boring.